Do you want to learn how to predict the future? Are you looking to master time series analysis and forecasting? Well, I think you're definitely in the right place. Over the next several hours, I'm going to show you everything that you need to know in order to explore time series data. We will go and dive deep into concepts like seasonal decomposition and as well auto and partial autocorrelation. As well, we are going to build our first models using exponential smoothing, but we won't stop there. So we'll do simple, double, triple exponential smoothing, also called Holt-Winters. As well, we are going to focus on the ARIMA family of models. So ARIMA, SARIMA, SARIMAX, and as well learn about cross-validation for time series forecasting and as well parameter tuning to really get the best SARIMAX model that we can do. We're going to do everything step by step. So if you want to code with me and you want to do the things that I do, you're welcome to download the course materials absolutely for free. And you have a link in the description and as well in the first comment. And to give you a nudge, to really point you in the right place, I will encourage you that to stick until the end, because at the very end, I'm going to share with you a couple of gifts that I have for you in order to really encourage you to keep going. So this is it, and I'll see you at the end. Welcome to this video where I'll make this game plan for our introduction to time series forecasting. The thing is that we are going to talk about this new type of data. Well, not really new, but could be new for you, which is time series data. Have you ever heard of it? It's all about looking at how things like stock prices or the weather change over time. And guess what? We are going to tackle it with Python. So don't worry, if you're new to this, I'll guide you every step of the way, and I promise you it will be fun. First off, let's discuss what is time series data and what does this really mean. Imagine that you're keeping track of your daily coffee spending. That's time series data. Anything that records how things change day by day, month over month, that is time series data. Now, the cool part, we are going to use Python for all of this. We'll start with the basics and you'll be amazed at how much you can do with just a few lines of code. I think you'll be quite happy with how much we can achieve just in this section, which is an introduction. We'll get our hands dirty by sorting and playing with data. It's really like putting a puzzle together, figuring how to do it. We'll look at patterns and trends. For instance, can we understand why Bitcoin's price skyrocketed last week, or why do sales dip every July? You learn how to spot these patterns. And of course, we'll draw some graphs. Not just any graphs, but ones that really tell a story. You learn how to turn numbers and dates into cool visual stories that anyone can understand. Ever wonder if you can predict stuff like stock prices? We'll talk about that too. It's a bit like trying to guess the end of a movie, but with data and trends. And to wrap it up, we'll look at real-world examples where forecasting didn't go as planned. It's really about looking at someone else's mistakes, and trust me, there's really a lot to learn there. So, are you in? Let's get started. In this video, we are going to dive deep into time series data. And I'm also excited to introduce you to a particularly intriguing dataset, the Bitcoin price data. So this dataset will be the central focus of our tutorials. It tracks the daily price of Bitcoin spanning nearly a decade, from 2014 to 2023. Now, why Bitcoin price data? So Bitcoin, as a pioneer of cryptocurrencies, does have a rich and dynamic dataset. Its market is known for volatility, rapid price changes, and significant trends. making it an excellent subject for our time series analysis. By studying this dataset, you'll gain insights not just into Bitcoin's price movements, but also into broader financial market dynamics and investment behavior. Now, let's understand the essence of time series data. Time series data is unique, and I really want you to understand why. It's like a chronological story, where each data point is a movement in time, neatly lined up from the oldest to the newest. You'll often find this data captured in consistent intervals. Think daily, weekly, or monthly snapshots of data. If we are to explore its wide-ranging applications, time series data isn't just about finance. Imagine its use in weather forecasting, where it helps to predict rainfall or temperature trends. In economics, it's crucial for analyzing GDP growth, and in healthcare, it's used for monitoring patient heart rates over time. Now, let's go deep into unique statistical tools. Time series analysis introduces some fascinating statistical concepts. Together, we'll look at autocorrelation, understanding how a data point is related to its past. In fact, time series data is very unique because we use data in the past to predict the future. Moreover, we'll discuss seasonality, identifying patterns that repeat over time. These concepts are key to accurate forecasting and trend analysis. And as we step into this journey through time series data, I encourage you to think about how this knowledge could enhance your projects. What questions do you have? Do you see any practical application about what you are learning? Feel free to reach out in the Q&A or the student communities. I'm here to help. Until the next video, have fun. Hey everyone, in this video we are going to kick off our time series forecasting Python activities. Please come to the folder, and then here you'd have the time series analysis folder. We'll kick it off there, and then introduction to time series forecasting. You have here two different data sets, the Bitcoin, that is our main one, but we have one that we'll also practice as well. Let's click on New, More, and then Google Collaboratory. For this video, we are going to focus on the libraries and the data. And that is just this easy introduction video where we kind of do the setup, just get really accustomed here. And then from the next video on, then we continue. And let me set first the working directory and mount the Google Drive. Here you go. It may happen that something like from google.collab. No, so for me it did not appear, but it may happen to you. Something like this: import drive and then drive dot mount, and it should be very similar to me, but something like this: content and then /drive. Now, for me, it did not, so I won't worry too much about it. And let me just add here a section on libraries and data. Here we go. And let me do Shift Enter. Now, to change the directory, it's %cd, and then you include the path. So I go to drive, my drive, and then Python time series forecasting. And then I go to time series analysis. And then I get introduction to time series. Copy the path, go here, Control V, and Shift Enter. To load the data, we need to use Pandas, so load the data. And let me add here as well another step just for the libraries, where I'll pop them here whenever we are using them. But import Pandas as PD, Shift Enter. And then here, load the data. So data frame equals to pandas read _ CSV. And then I would include the Bitcoin price that we have here. So Bitcoin price. And this is where we get all of the Bitcoin data since 2014. all the way to the end of 2023. So let me put it there. Pandas read CSV Bitcoin price dot CSV. Let's have a preview. So data frame dot head, shift enter. And we have quite a few KPIs here. We have the date, open, high, low, the close, the adjusted close, and the volume that was traded. Now, there is something which is very specific to time series, which is the time. And it's important that we focus a lot on this time series index. And in the next video, I'm going to show you some tips and tricks, some ways of dealing with it. And this is where we really go into the nitty-gritty, where we really start to explore this world of time series. Until the next video, have fun. Welcome back. In this video, we are going to cover the times series index. Currently, we have here the column date, but Python does allow us to have date here as the index, and it kind of transforms all of our pandas data frame into this time series type of data, which becomes much easier to manipulate, visualize, and explore. So let's kick it off. Let's have a look here at our date, and what I want in the end is to convert date and then to date, time, and set as index. So it's a two-step process, index. Let's have a look. So if we go to our data frame and then date, let me do Control Enter, we have it here as an object. And with pandas, we have the possibility to transform to a date time type of object. To do it, pandas dot to underscore date time, and then we open it. And then what we can do, we don't really need, but we can add format and then equals to, and our current format, it will be percent year and then percent month and then percent day. Now let me close this, and here we have it. It would then be transformed into this date time object. Let me make the transformation here. So data frame and then date equals to this. And now if I want to set it as index, I would do data frame set index, and we would go here, we would include date. And let me do data frame dot head and do shift enter. And it's not as index, so let me make some changes here. So let me go to my set index and see what I can do. And let's explore. So set the data frame index using existing columns. Set the data frame index row labels using one or more existing columns, or erase. The index can replace the existing index or expand on it. And let me check here. So drop default equals to true. So delete columns to be used as the new index. Yeah, kind of what we want. Whether, so in place, whether to modify the data frame rather than creating a new one. Actually, this is what I want, but the default is false. Let me correct that. In place equals to true. And let me do Control Enter. And here we have it. Now, yes, it is exactly as I wanted it to be. We have here the date as the index. And this allows us to actually explore our data frame in a much quicker way. So for instance, imagine that I want to have a look at our Bitcoin data for a specific period. So let's say select the Bitcoin data. I think the last all-time high, at least at the time of recording, was November 2021. So select the Bitcoin data for November 2021. And let me show you how to do it. If I go to my data frame And then here, you just include it as a string. So let's say that I want to start with 2021. Here we go. We have here all of the data as 2021. There's a future warning. Let me have a look here. Indexing a data frame with the date time like index using a single string to slice rows, like, frame string, exactly how we are doing, is deprecated and will be removed in the future version. Use frame.lock. Okay, here we go. Okay, I can do that. So basically this way that I'm accustomed to will be deprecated. So I should use .lock. Let me do Ctrl Enter. Future warning is gone. And now we see the data for 2021. You can see 365 rows because Bitcoin prices are available and traded every single day. And I wanted November, so I just do 11. And here we have it. We have for the 11. And if we wanted a specific day, and I think the all-time high should be somewhere around here. So I have 09. Here we go. Let me put 09. This is how we could do it. Now, I've shared here that we have done this by setting the index, but you can actually do this by loading the data and setting the index. Here we go. Let me show you how to do it. It's super, super easy. So imagine we go to our pandas and then read _CSV. We take our Bitcoin price data, Bitcoin price dot CSV. So this is our initial starting point. And then I would go here and I would get my index call. Here I can specify, hey, it's called date. Here we go. And let me store it just so that you see. So data frame 1 equals to this. And imagine, let me check the index. So data frame 1 dot index. Here we go. And here we have it. So we have the index. So data frame 1 dot head. And here we go. So it is exactly like here, but one key difference. I don't know if you noticed. Maybe I was too fast. I was definitely way too fast. But maybe you could have noticed that. Okay. I need to get rid of the parentheses. Here in the index, it's an object. So I must also tell Python, hey, this is not an object, this is a date. And what we can do is just go here and parse dates equals to true. And what happens is that Python will now go and try to set the dates into this format. Now, from our perspective here, this format and the initial format as well, so this year, -month, -date, this is the most common and this is the standard. But in case that you don't have this format, if you include parse dates, so first Python will see that it is a date and then will try to transform it as well into this format. We don't have it here, but in future sections, we'll deal with multiple types of dates and so on. We'll explore it further. But this is just an FYI for the future. Last thing I want to show you, and there's a plurality of things that we can do. So what is called this resampling to monthly or weekly. I'm going to show you both. Monthly frequency, and calculate the mean closing price. And here we go. So imagine that we would be like, yeah, you know what? This thing about looking at it at the daily level, it's way too much. So what we do is that we can resample to a monthly level and just look at the average. So dot mean parentheses. And here we have it. So we just have here one observation per month. And this is representative of the average for that specific month. And if I have here a month, I can also have a W for weekly. This is also a possibility. And then we have data on weekly level. Again, this is one of the many things that we can do as we explore our time series data. I'm going to show you more and more and more. but be warned, it's a lot of things. So if you can think of one thing that you would like to do with your time series data, there is a way. And hopefully I'll show you all of them. But until I do, or if I don't and you have questions, let me know. I'm here to help. And otherwise, I'll see you in the next video. Welcome back. In this video, we'll start exploring the data. Let me add here exploring data. And here we go. Let me start with this, which is called the 7-day rolling average. This is very common in time series because what we are doing is that we are basically smoothing out the data. Let's have a look. So 7-day rolling average of the closing price. And to do it, we start by going to our data frame close. Here we go. And what we do, there is this very handy function, dot rolling. And here we specify the window. And what we want is, because we want a 7-day window equals to 7. Now, if I just do this, this is really still not enough. We kind of need to specify. And we have prices, so mean is really the most appropriate. So parentheses, here we go. And of course, for the first few days, we don't really have anything. So that is a nan value. But for the last ones, we do have. Now, let me store this. And data frame, I'm going to call it a 7-day rolling average. Pretty straightforward, right? 7-day and then rolling, and this should be enough. Now imagine, let's have a look. So if we were to put here data frame, and then if we were to get here our close, and then comma, and then the 7-day rolling, let's have a look. Now, if we want to have a deeper inspection here, the best way is really to visualize it. And we can just do dot plot. And let's do it. Now, the thing is that it's really a lot of data, right? I told you that it's supposed to smooth out, but it's just so much. So one very simple way is, okay, how do we actually just look at it at just parts? And we can just go here. We can do these square brackets. And let's say, let's have a look at 2023. And here we go. Let me do Control Enter. And yes, we are having our future warning. So let me do dot lock. Hopefully it should be here. And here we have it. Now, one thing is that I see here our access. I need to import a library. This will be very helpful for us, which is the matplotlib. And let's go there, import matplotlib.pyplot as plt. Let me do Control Enter. Now let me navigate to our exploring data part. And let me do here plt.show and Control Enter. I'm I'm definitely already going into the next lecture on data visualization, but I promise there's still a lot more to cover on this. And a couple of things here, right? So first, you can see that our orange, which is the 7-day rolling, this is a bit smooth out. This is what averages do. They smooth out stuff. And at the same time, it kind of feels like there's a delay here. And that's really the truth, right? With a 7-day rolling, with moving averages, it's always like a delayed KPI. It takes a few days to actually catch up. That said, we can actually move on. Let's say that we wanted to go here and we wanted to find out the highest average month. This is super, super easy because we already know how to do this average month. And let me get it here. And let me put it back here, and we have the mean. And let's say that we will just go. So first, let me do Control Enter. And we have this part. And what we would do, let's say we go to close. Here we go, Control Enter. Then now that we just have the close, we do .idx max and parentheses. And here we have it. We are actually finding here, we still have weekly. So let me find and change here to M. And then we see here that the month of November from 2021, this was the month with the highest values on average. Another thing, and this is super specific to financial data, is that you can calculate daily returns. Daily returns. Here we go. If I go to our data frame close, and the way that returns work is that we have the value of today, and we divide by the value of yesterday, and then -1, and this leads us to the return. So if I have 101 today, and yesterday it was 100, this is a 1% return. And there's a very easy function, which is the percentage change. Here we go. Let me do here, Control Enter, so that you see. And this is the percentage change. And you see that the first one, this is always an AND, right? Because the first day does not really have a return. But for all the others, they do have returns. And I kind of like to always have this times 100 because it's a percentage. And therefore, I like to see -7%, -3, or whatever. Now, let me store this. I'm going to call data frame, I'm going to call it daily returns. Here we go. And let me do Shift Enter. And one thing that we can explore here is, let's start to have a look at the volatility. And for instance, we could see here. So I want to see the days with more than 10% change in closing price. And the way to do it is that, imagine, we already know how to do this filtering. We would just do data frame and then go to our daily returns. And then let's say bigger than 10 or less than -10. So imagine I would start here. And I could just do like this, put this in parentheses, and then or better yet, or less than -10. But there's an alternative here, which I want to show you, is that you can just take the absolute value. So ABS, and basically this is going to transform every value positive. And then doesn't matter if it's positive or negative, as long as the delta is bigger than 10, this is what we would get. And we kind of see that there's 97 rows here, so 97 days, where we had daily return that was above 10% or less than -10%, which is definitely fascinating, right? So these are really, really, this data is really volatile. And with this, I'm actually going to stop here. Let me do .head just so that we don't have an output that is so big. And in the next video, we are going to focus on data visualization. Welcome back. Let's focus now on data visualization. Let's make a few plots with our Bitcoin data. To do it, so the first one, which is always like the simplest one, let's take our daily data, so our daily closing price, and plot it. To do it, we go to our data frame, close, and then .plot. This is the simplest version of it, and here we go. And we can also do, so first plt.show so that it looks a bit nicer. And as well, it's always a good idea to add a title, daily closing price. Let's do Shift Enter. And here you go. We can see a spike in 2018, here as well a spike or two spikes in 2021, and now this new increase that is happening, or at least, it's happening at the end of 2023. I think now it's a bit of cooling down period currently. Not cooling down, but it's just stable. Let's move on and let's go here. And for instance, we have had a look here at our, let me see, here you go. Let me get this part here, this resampling, Control C and Control V. So I want to plot the yearly volume. Here we go. Volume. And I know that I copied, but I'm just going to do it myself. So data frame, resample, because I need to change the KPI, the resampling is just, it's not easier, but it's as good. Let's do a sum here instead of the mean, and then the volume. Here we go. Volume, and let me do Control Enter. So this is the volume here, and then if I do dot plot, here you go. And here we see the volume that it kind of spiked in 2021. Now, I might add that it's this part here on the volume, it may not be 100% correct, at least from what I see online. As I look into the libraries that I use, the data, I think the volume part may not be 100% correct. But again, the goal is to show you how to do it. But please have in mind that any type of data that you use, always triple check that it is the actual data, that it is real and true data. And last but not least, our plt.show and parentheses. Now, I kind of want to, again, I'm going to focus here on the volume because I think it's an interesting KPI. So first, what I want to do in the end is to plot closing price and 30-day rolling volume. So I want to see if there's any kind of relationship between these two variables. One, that is the closing price, and the 30-day rolling volume, which is this transformed KPI that we are going to build. Data frame 30-day rolling volume equals to, we go to our volume, and then we apply the rolling method. We specify window equals to 30, and then the KPI mean. Now, to plot it, it is as simple as taking this. We would just go here and do dot plot, and one thing that you can add is legend equals to true. So this is step one. And here we go. Here we have it. Now, one thing that I like to do is, because these rolling KPIs and the closing price, in terms of the KPI per se, they are very different in terms of magnitude. What I do is that I'll put the other KPI in a different axis. So I'll start using this axis so this AX for axis, and then data frame close, and then dot plot secondary Y equals to true. And here you go. And legend equals to true. Whenever you have more than one, it's always important to have here the legend. So this is step one. And now let me do plt.show. Here we go. And this is actually it. You can also go here and would be, for instance, AX and then dot set Y label. So this first one would be the volume. here we go, Control Enter. And let's have a look. So we can kind of see here that there seems to be some kind of relationship, because it's going up, it's going down, it's going up. Here it looks a bit weird, but again, up. Again, a lot of trading here as well, but not a lot of volume per se, but a bit. And it kind of feels like there could be a relationship. And to do it, let me show you how this actually works. What I would do is that I would take, so data frame, I would take the close, and then I would just go here to the right. I'll get my 30-day rolling volume. I think it was just VOL, right? Here we go. Let me do Control Enter. We have it here. Let me do .core. Here we go. And here we have it. So this is the correlation between the 30-day rolling volume and the closing price. So this indicates that the price is heavily connected to the volume in a positive way. The higher the volume, the higher the closing price, and vice versa. With this, I'm going to stop here. This was a way to also wrap up and see, hey, we had some insights from our chart. Let's also get some data analysis here as well. And in the next video, we are going to focus a bit on data manipulation. Until then, have fun. Welcome back. Let's do this component on data manipulation. And one thing that we can always do is to identify missing values. Here we go. And to do it now, so imagine data frame is null. We can just start there. And this gives us a false and truth. So you can also do .sum. And then what happens is that you get missing values for each of the columns. And for instance, the 30-day rolling volume has 29 missing values. Now imagine that we would like to not have missing values here. We could find a way to fill them. So fill missing values. And for instance, we could go to our data frame and we go to our 30-day rolling volume. We do .fill and A and method here. And let me see if there's something here in the documentation that can really help me. So here we go. We have backfill, B-fill, pad, F-fill, and none. And here we have something to clarify, right? So method to use for filling holes in reindex series, pad/F-fill, propagate the last valid observation forward to next valid. So it means that it would take the ones from the past, propagate to the future. And then we have backfill/B-fill, which uses the next valid observation to fill the gap. So this is also a possibility. For us, let's use the backfill, right? So we take one from the future and propagate it to the past, because we also know that all of this, they are the first 29 observations where we don't really have a 30-day rolling volume. So here, B, fill. Now, let me do Shift Enter, right? And then if we were here to identify the missing values, let me do Shift Enter. We still have, okay, sorry. I forgot one thing, right? So we have the method bfill, and we can store it under this variable, or we can also use, so in place. So this makes the changes in the data frame. equals to true. And then let me try again. And here we have it. So now we no longer have missing values in the 30-day rolling volume variable. So this was one of the things that I wanted to show you. Another way, so another alternative here is that you can interpolate missing volume, or better yet, so in this case, let me take the 7-day rolling, and let me see if we can do it. So data frame, let's go to our 7-day rolling, and then dot interpolate. Here we go, parentheses. Now let me get here the help so that we can have a look. And oops, it went away. And okay, again, let me try. I wish there was an easier way. If you know of an easier way to get the help here, that would be mighty, helpful for me. Now, fill non-values using an interpolation method. Please note that only method linear is supported for data frame series with multi-index. We just have one index, so this is not for us. Linear, this is, okay, doesn't matter. There's no explanation. Ignore, and time works on daily and highly resolution data to interpolate given length of interval. Index values uses the actual numerical values of the index. Pad fill in NAND using existent values, nearest, and so on. So you can really have like a lot of options. For us, linear is usually the way to go. So in place equals to true. And here you go. And have in mind, so what will happen here is that nothing actually happens because, and I should have actually clarified this at the beginning, right? So this interpolation, what happens is that it focuses on the index per se. So here we're filling NAs. The interpolation is when you don't have the index. And this is what it happens. So if you don't have a specific day in the index, this will go there and put it with the linear method. That said, let's continue. And here, what I want to show you is how to extract time variables. Here we go. For year, so if we were to build data frame year, we would go to our index dot year. So this is one. Data frame month. This will be the same, right? So data frame dot index dot month. And if you wanted the day, can you really guess what it is? I'm sure you can. So equals to data frame dot index dot day. So this is easy. And let me do data frame dot head so that we have a preview of what is happening here. And all the way to the end, year, month, day. Now, let's do, for instance, day of the week. Day of the week, so data frame and then week, day. We go to our data frame, dot index, but here there's a slight change. Day, name, and then with parentheses. Let me show you, right? And now we have there the weekday. And last but not least, let me show you, for instance, this one. So data frame, and then let's say that we want to flag is weekend. We would then go here, and what we do is we go to our data frame, and then dot index. And actually, let me show you this one before. Another way for you to do the weekday here is that you can do, and let me show you here. So this would be weekday numeric, and this would be, instead of day name, it would be weekday. Let me do Control Enter. Let me put this one here as a comment. And here you go. Let me go there. We have here a weekday numeric. Wednesday is at 2. So it's 0, 1, 2, 3, I think. Let me confirm. And the best way to confirm is that we kind of should go to the weekday here. Let me actually grab it, Control C, and then let me Google it because we're not getting any help here. And here you go. So we have weekday. Let me go to the documentation. The day of the week with Monday equals to 0, Sunday equals to 6. And this is what it provides. Therefore, imagine that we want to do is weekend. What we do is weekday. So weekday. And then you do bigger than. And oops, not that one. Bigger than. So 0, 1, 2, 3, 4. So this is Monday to Friday, so bigger than 4. Let me do dot head here, and let me show you. We have false, 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 true, true. So the Saturday and Sunday have been flagged. And then the last thing, so one thing that's super common when it comes to feature engineering is how to do lagged values. And let's say data frame closed and then lag 1. The way that we do it, it's super easy. So we go to our data frame and close, and then we do shift 1. And this is it. And then imagine, right? So you want to do 1 and you want to do 2. And you can just do this, and it's as easy as this. And if you want to do multiple, you can do a for loop and so on. Again, it's super, super easy how to do it. And just keep this template close to you, or ask ChatGPT. Even if you Google it, it should be super, super easy to find it. Just have on your mind what you need, and then with a very quick search, you can definitely do it. This is it when it comes to our data manipulation. Now it's time that we learn a bit more on how to get to know our data. Until the next video, have fun. In this video, I'm going to introduce you to seasonal decomposition. The general idea is that you separate the time series data into 3 components: trend, seasonality, and the error term. Let's look at each of them individually, starting with a trend, which is the general direction of the time series. Imagine the following chart representing the trend. And one important thing is that the trend can change over time, but not every day. That is no longer a trend. Next, we would have the seasonality, which are the seasonal cycles. Think about a time series that is higher during summer and lower in winter. Imagine the following chart with a seasonal curve like this, which is constant over time and cyclical with some kind of amplitude between the top and the bottom. And then lastly, we would have the error term, which is what is not explained by the trend and seasonality. It is supposed to be a random walk without really a pattern, like this chart. Let's zoom in now on seasonality. One thing to know is that there are 2 types of seasonality. The first one is additive. It is characterized by having constant seasonal fluctuations. And as an example, it will mean that we're always adding 10 units in July or subtracting 50 units in December. We can see this example where the seasonal fluctuations are the same when the trend is low, medium, or high. The other type is multiplicative. The key definition is the seasonal cycles that are proportional to the trend. And to illustrate, we talk in percentages, like increasing by 10% in July or decreasing by 50% in December. In this chart, we can see, despite, my poor drawing, some fluctuations that increase over time. Now, why does this matter, could you ask, right? So by understanding if our data is additive or multiplicative, we can better predict future moves and make better informed decisions. And one question that you also may have is how to identify which seasonality type your time series has. And fortunately, there is no statistical test available that will tell you what it is, but you have two options. The first one is data visualization, as we did already, to see if the time series has constant fluctuations or whether they are kind of proportional to the trend. The other option, and this one is also very good, is to focus on the model performance, which means creating two different models to see which type of seasonality fits best the time series. The best part, we'll do both every single time to check which one is better. Though keep in mind that option 2 is generally preferred as we should be results driven. So if you think about it, option 1 is you look at it before, you make this assessment, and then option 2 is you look at it after. So you model, you forecast, you check the results. And in general, that is actually preferred. Of course, we will try both, but let's see how this actually works. Let me show you how to check for seasonality and plot it in Python. Until the next video, have fun. Welcome back. Now let's cover seasonality here in Python. And the thing is that when it comes to time series, most of it has this seasonal component. And this represents these repeated cycles that happen in our data. Can be in our daily data, weekly data, monthly data, and so on. And this is something that in general makes total sense, right? We have this rhythm throughout the day, this rhythm throughout the week, maybe even a rhythm throughout the month, and definitely a rhythm throughout the year that is cyclical, and it's often represented in data. Let's start here by visualizing, and there's this very cool plots from stat models. So I go from stats models dot graphics dot TSA plots. I import, I'm going to do the month plot and the quarter plot, which will be the focus for this video. Here we go. Let me do Shift Enter to make sure that everything is okay. Okay, and here we go. Now, to do it, and let's start with a month plot. Month plot. Here we go. Now, this is going to give us this monthly seasonality. And what we need to do, and let's put here plotting the monthly seasonality. Here we go. And inside, what I need to do is I need to take my data frame and the variable of choice, in this case, close, and I need to resample it. Resample and to a monthly cadence, right? So, and then I do dot mean. Dot mean. And here we go. Let me do Control Enter so that we can have a look here. And what else can we actually do? So let me actually customize here our chart just a little bit. And so Y label. And okay, let me get rid of the help. Y label. Okay, not this. Y label equals to, and let me put closing. Closing. And here you go. Let me do Control Enter. Here we have it. Now, what does this represent? So there's the red part and then there's the black part. The red, these are the average values through time. And in general, it should kind of represent some kind of seasonal curve, which in this case is extremely tiny. This is not really a seasonal curve because there's barely any variance. It's most likely that these ups and downs are more due to the bottoms of specific years rather than anything else. And then the black lines, so these represent the values for each of those months for all the years. So for instance, take January. This line represents all the January values that we have. I think we have January values. I don't know if it's from 2014 or 2015, but all the way to 2023. And this is what all of them represent. Now we have this part here. We have two. So let me include here plt.show. This will hopefully get rid of the duplicated chart. But just to conclude again, to reinforce, it does not seem that we have a seasonal curve. So at least that would be my general interpretation. Could be a tiny bit, but to be fair, like if you take here the April, right, everything is really around the same levels. Next up, now let me do the quarter plot. Let me also take advantage of this. Let me do Control A, Control C, and then Control V, plotting the quarterly seasonality. Instead of month plot, I do quarter plot. And instead of resampling to M, I resample to Q. Let me do Control Enter. And here we have it, right? So here it's even clearer that our seasonality is really not there. For some reason, Q3 is low, but it's really, really flat. And you can see that there's so much of a higher variance in the black lines versus the red ones. Now, let me show you, because I have a different data set. So financial data like we have here is not really known for its seasonal curves. And I didn't want to leave you here without, actually seeing what would be an actual seasonal curve. Let's load new data. Data frame. It's this Choco customer monthly revenue. And it represents for each of the months how much revenue there was. So let's have a look. Data frame underscore Choco. It's Choco because it's from a company that sells chocolate. That is the case study there. Read underscore CSV. I put here my Choco monthly revenue. And then let's start there. Data frame underscore Choco. Let me do Control Enter. Tiny error. So I'm missing. And here you go. .csv. Try again. We have here the dates. Let's focus there. And let's do index col. So for column equals to, I can put month with year, but I can also just put the index number, which is 0. So that's the first column. And then parse dates equals to true. Let me do Shift Enter. Here we have our data. Let me do .head because the output is really long. Control Enter. And here we go. Now let's copy here our month plot. So let me, what am I doing? Okay, Control A, Control C, and all the way to the bottom. And instead, so we no longer need to resample because we already have monthly data. So data frame underscore Choco. And then we have the revenue while label is revenue. Let me do Control Enter. And here you go. And this is more like a seasonal curve, right? So with ups and downs, and there's like a larger thing, for instance, for November, February it drops. This is more of a deeper seasonality curve. Here you see that it matters a lot when you are predicting. Like it really does make a difference. And before, it doesn't really make a difference here so much because it doesn't really go all the way up or down. So this is how you'd actually interpret this, and this becomes much more apparent with this kind of charts with data in terms of revenue from actual companies. And with this, I'm going to stop here. So this was part 1 of our seasonality focused on these plots. In the next one, seasonal composition. Until the next video, have fun. Welcome back. Let's now focus on seasonal decomposition. And let's go here. Let me import something else. And here you go. From stats models. Stats models. Okay. Stats models. Here you go. Dot here. TSA dot seasonal. Let me import seasonal decompose. Control Enter. And yeah, it is working. Let me now go here and let me show you. Seasonal decompose. And let me take here, for instance, our data frame close. So we're going to focus first on the Bitcoin data. And close. And then I include here my type of model, so multiplicative or additive. And have in mind, again, multiplicative is when our data grows or the fluctuations are also exponential over time. And additive is when the seasonal fluctuations, they are the same in absolute, so they don't change over time. Multiplicative is for me one of the most common. At least I find it much more common than when I have a look at, if it's additive, I don't usually see it. Multiplicative, it's usually very obvious. And yeah, as you'll be able to see. So let me actually see if we have a look. So, okay. So for instance, for this kind of data, you don't really have a seasonality. And when we focus on the Shoko customer revenue, there I think we'll be able to see if it's additive or multiplicative. That said, we have seasonal decompose. Let me also ask for help because I was forgetting about that. Let's see what the documentation says. Seasonal decomposition using moving averages. We have the X. So this one is important. X must contain 2 complete cycles. This means that if you have daily data and you want to have, the seasonal cycles of 2 years, of 1 year, right? You need to have 2 years. However, if you just want to have a look at the weekly seasonality, you need 2 weeks. And if you have weekly data, you need 2 years as well, monthly data as well. So you always need 2. So let me go here and okay, no, I closed it way too fast. Let me go back. So loading, opening tab, and then let me see if it's easy to spot here. We have a frequency somewhere and period. So period of the series must be used if X is not a pandas object or if the index of X does not have a frequency. Let's set it just in case. But you have 2 options because we have daily data. You can have period equals to 365. I think this one is interesting if you want to have a look at the yearly seasonality. If you want to have a look at the weekly seasonality, then you set to 7 because there are 7 days in the week. So let me go here, 365, Control Enter. And this is where it is stored. Now, let me come here. And what I want to do is this decomposition and store it there. Decomposition. And I actually wanted to do this before because now I need to align everything, but doesn't matter. Let's do it. Align. And let me also add some comments as well. What we're going to do is seasonal decomposition plots for Bitcoin data. And then if we do plots, so let's go here and it's this fig. Here we store the plot. And why we store the plot? Because I want you to play around with the size. decomposition.plot. So this would be enough already to plot if you just include decomposition.plot. Yeah, but I'm going to go here to our fig and set size inches. And let me put here 10 and 8, and then we'll play around with it to see how it works with our current zoom. And Control Enter. Currently running, and it will pop up eventually. And here we have it. So I think this size is okay because we have a look at them. Or better yet, we don't really need to have a look at all of the charts at once. This is okay. Another thing why I like multiplicative is when you have here the seasonal components, you can look at them from a percentage situation, right? So we know that according to this, it varies between 0.9 and 1.1. So a 10% variation, it's not really a lot. But this is how you can see. And this is easy to see. So if I were to do it with additive, let me show you what I mean. You can also, I think you can just put add. It will also work. And okay, it's taking a bit of time, but here you go. And here you see the seasonal. So minus 2K, plus 2K. It's also a bit more difficult to interpret like this. So let me just put mul. Will mul also work? Let me give it a try. Okay, yeah, it's also working. But let's have a look. Let's try to interpret this. So we have period 365. This means that we're looking at yearly seasonal curves. And you can see that it's also not really a smooth data. And for several reasons. But if anything, it's because you have this second seasonal cycle, which is the weekly data, which is also here. If you wanted to have a look here, so let me put, for instance, period 7, and we can see the differences. So here, our focus is on the seasonal, which is massive. Also, you can see the percentage. It's really, really tiny. It's basically telling us there's not a seasonal curve, at least for a weekly data. And then the trend becomes less smooth as well. And so this is another thing to see. When it comes to modeling, 7 is usually more common. So when we go and we do Holt-Winters or SARIMAX for daily data, 7 is more common. Now, let's go here and let's go to the next one, because another thing that I want to show you, right, is with the other data. So let me go here and let me put it below. Seasonal decomposition plots for chocolate revenue data. So data frame underscore choco, and then our variable, it's called revenue. Model multiplicative period. We have monthly data, so our period is 12 because we have 12 months in a year. Control Enter, and let's see. So this is our actual data. I don't think we have seen it before, but this is our actual data. And you can see that it grows over time, point 1, but also the seasonal cycles, they really increase over time as well, right? You can see that the amplitude between the top and the bottom really increases over time. And therefore, I would be very confident in saying that the seasonality that we have here is multiplicative. You can also see here the seasonal cycles, a bit more detailed here with spikes, much more clear when it comes to the seasonal curves. And just to wrap it up, let me add here, when it comes to seasonality, this is what you would set. So you have 24 for hourly. This is the most common. Then we have 7 or 365 for daily, but 7 is preferred for modeling. You'll even see in the documentation when we use, I don't know if it's Auto-Winters or SARIMAX that have in the documentation use 7. And so modeling, I think it's just one L. So 7 or 365. Have in mind that if we have hourly and we have a lot of days, right, you would have 24, 7, or 365. because you just really get another cycle there. Then 52 for weekly, 12 for monthly. Then you have for quarterly, And then another one, this is very specific, but you have 5 for weekdays. And this is it. When it comes to seasonality, we can now see if we have seasonal curves or not, how they interact, where are the spikes. And now it's time to shift gears, go from understanding the seasonal cycles to a key aspect of time series data, which is that there is information in the past to help us predict the future. And this is where autocorrelation comes in. Until the next video, have fun. In this video, I'll introduce you to a super cool concept, which is the autocorrelation. The basis for the concept is to find out whether there is information in the past to help us predict the future. And to do it, we correlate the values of the time series with its lagged or past values. To see how it works, imagine these two axes, where we plot the observation with y at times t and against y at t minus 1. This means the period just before. The data points show a clear upward trend indicating a positive correlation. We then compute the correlation of both series and imagine that the correlation value is 0.8. We then start to create the main graph with the correlation value in the y-axis and the number of lags in the x-axis. We move then to the next lag, which would be lag 2. We plot the time series with the values lagged 2 units of time and check the correlation, which is, let's imagine, 0.6. We again plot it in the graph. One key idea here is that we would always expect it to be lower, since the information is further in the past and thus not as relevant, which would translate into a lower correlation value. Hence, as we continue to compute the correlation values of the time series and its lagged values, we will get lower and lower values, maybe even negative, but definitely closer to 0. And it is by analyzing a chart like this that you can see how long in the past can you go and still find relevant information. Of course, this is not all of it. This is just part of the picture, as we'll be able to see, but it's a very important data point. And to summarize, the autocorrelation plot will tell us if there is information in the past and for how long. Let's apply it and see how it works. Until next video, have fun. Welcome back. Let's focus now on autocorrelation. Autocorrelation. Here we go. And let me come here to the part where we imported the plots. Let me also take them from here. I think it's better from an organization perspective if we put everything here at the top. And let me close this part. And we have as well, so it's the same, but it's becoming too big. So let me repeat here and then Control V. And I'm going to import, it's called plot and then ACF. Here we go. Let me do Control Enter. Let me go here to our autocorrelation part when we had this. And as well here, let me get rid of this cell so that everything is organized and cute. Now all the way to the bottom again, and let's do it. We're going to plot the autocorrelation, so ACF, and plot the autocorrelation, right? And to do it, let me also customize it just a tiny, tiny bit. So figure and then axis and then PLT subplots. Plots, here we go. And then we specify the figure size. And this really allows for a better customization so that you really tailor to your window. And then let's do 10 and 6. Let's see if it works. And I'm doing something wrong. PLT dot subplots. And this also means that we have an extra parenthesis here. And then plot, okay, oopsie. Okay, plot ACF. And then inside, we are going to include our data frame close. And then we need to specify how many lags we want to see. So let's put 100. This seems like a very solid number. And then AX equals to AX. And okay. And then, yeah, PLT.show. And before you do it, let me ask you, what are you expecting? High autocorrelation, low autocorrelation, and why? So the truth is that it is massive, right? So above 0.75, even after 100 days. It's huge, like absolutely massive. You can also see this area which has a fill, right? So this represents the confidence interval, so to speak. So if these dots were within the area, it would mean that they would not be statistically significant. This implies that all of these autocorrelation values, they are statistically significant. And just so you know, so I'm aware that this is not a statistics course and it's not meant to be a statistics course. But for those who don't know what is statistical significance, a very simple way of describing it is basically saying this value did not happen by chance in a very, very simple way. It's most likely that, the impact or the relationship, in this case, it's relationship, it's very likely that the relationship is there. So we have done this for our close, and I'll come back to it in a bit. Let me just do now for our Choco. So data frame Choco, and let me put here revenue lags. Let me put 30, right? Because 100 months, that would be quite a bit. Control Enter. And here you go. So this is more what it looks like. And just so to highlight, so we have 1, 2, 3, 4, 5, 6, 7. You would see when it comes to this monthly data that you usually have a spike 6 months before and 12 months before. This goes to show the seasonal curves. And then you'd also see a very high autocorrelation value for the month before, maybe 2 months before. This comes to show that, there's information in the immediate past to help us predict the future. And then the spikes 6 months and 12 months in the past, there's information in the seasonal cycles to help us predict the future. Now, there's an issue with the autocorrelation. It's not really an issue, but it's an incomplete type of KPI. And spoiler alert, there's something that goes well with the autocorrelation, which is the partial autocorrelation, which we are going to see. But the main issue is that, just to help you illustrate already from this video, is you look here at the lag of the third month, right? So already at 1, 2. So this is the second month in the past. And the thing is that this correlation is influenced by the correlation of the month before, per this definition of autocorrelation. And the thing is that you kind of need the partial autocorrelation, which cleans out this effect. And this is what I want to cover starting in the next video. This autocorrelation is telling us that there is a lot of information in the past to help us predict the future for both the Bitcoin data and also for the chocolate revenue. But what can happen is that the correlation of 12 months ago is influenced by the correlation of 6 months ago. and the partial correlation will kind of fix that. The next video, we are going to go there, and with the autocorrelation and the partial autocorrelation, this can help us paint a better picture of how much information do we actually have in the past to help us predict the future. Till next video, have fun. Hey everyone, now that we understand the autocorrelation, let's go to the partial autocorrelation, which is a very cool concept in the world of time series. And don't let this scare you, right? It's not super complicated. It's really handy, and I'm going to break it down for you in very simple terms. So let's kick it off. What is this PACF, or partial autocorrelation function, all about? Imagine that you're trying to understand the relationship between your coffee consumption today and how much you drank a few days ago. But here's the twist. You want to know this without the influence of all the days in between. That's what the partial autocorrelation does. It tells you the direct relationship between your data points at different times, removing the effects of the points in between. Remember the autocorrelation function? That's like the total correlation between the series and its lagged values, including indirect effects. It's like asking, how does my coffee consumption today relate to all the past days? The partial autocorrelation, on the other hand, is like asking, how does my coffee consumption today relate specifically to 3 days ago, ignoring the days in between? So while the autocorrelation gives you the overall picture, the partial autocorrelation zooms in on specific direct relationships. When you plot the PACF, you'll often see bars at each lag, just like the autocorrelation. If a bar stands out significantly, it means there is a noteworthy direct relationship at that lag. If these bars drop off quickly, it suggests that only recent values have a direct effect on current values. If they tail off slowly or oscillate, it indicates that older values still have a direct influence. Now you can ask, why does it complete the ACF? Well, the autocorrelation starts the story by showing all the correlations, but it might include some noise from indirect correlations. The partial autocorrelation completes the story by isolating the direct correlations, giving you a clearer picture of how each point in time directly influences another. And that's it for the partial autocorrelation in a nutshell. Do you have any questions? And otherwise, I'll see you in the next video. Welcome back. Now that we have done the ACF, let's cover the PACF. Let me add it here, plot PACF, and let me do Control Enter. Now, let me go back, autocorrelation, and now let me include the partial autocorrelation here as a section, partial autocorrelation. Here we go, Shift Enter. Let me copy from here because it's literally 1p, the difference. So Control C and Control V. Here we have it. And then let me put here a P and same thing below. Let me get rid of the plots so it's a bit less messy. And let me do Control Enter, and now we can see the difference. Here we see that we just have information in the day before. So all the other correlations that we're seeing were most likely due to the correlations of the more immediate past. And therefore, if we are to try to predict Bitcoin price data, which is insanely difficult, cannot really rely on the information of 2 days ago. There is information there, but it's not super relevant. And this is what I want to share here. And still, this does not mean that, it's good enough, right? It does have a strong relationship there. This is what we're seeing. But just because there's a strong relationship doesn't mean that you can grasp the magnitude of the change. Now, let me go here to our, let me also change the comments, right? PACF, partial. Here, let me copy this part and then Control V to replace. Let me do Control Enter. And here you go. Let me also reduce, I think the size is too big. I want to try to have a look at all of it in one way. So let me, okay, and yes, okay. Let's have a look. So the month before definitely still has information. Apparently, what also can have information is so 1, 2, 3, 4, and 5. And then 6, 7, 8, 9, not so much. The 10th month apparently has some relationship, but then the 12th month we lose a bit. And then the 13th month also has some relationship apparently. But to say that it's one thing to look and the two things actually go together, because what we're saying here is that there is information in the past and there is information that we can use to try to predict. We can go 1, 2, 5, 6, even 12 months in the past. And then if we go to the partial autocorrelation, it does not mean that we don't have information in the past. It just means that maybe some of that information that we think is in the past is potentially due to other correlations that don't necessarily mean or connect to that correlation, 12 months before. Maybe the correlation of 12 months before is partially connected to the correlation that was happening 6 months before. And with this, just to wrap it up, you look at everything together. And what we're doing here is essentially getting to know the data. Let me also add here, introduction to time series forecasting. Between getting to know the data and then actually being able to create good models, this is a whole different thing. Currently, we have been exploring getting to know the data. And from here on out, we change gears. We'll always want to get to know the data. That is true. But we'll also want to forecast. And in that scenario, what we'll care is about results. This is it. And until next video, have fun. Welcome back. Just before we wrap up the Python part, let me start to create a useful code script. When it comes to using Google Colab, it's actually not as easy to go from one script to the other. It's one of the things I don't like so much about Google Colab, and it's much easier in other softwares for Python. In what you can do is that you can just create some functions and import from one script to the other. That is very easy. Here, not so much. And therefore, we'll have to go with a more, let's call it low-tech idea, which is to use this useful code. And let me come here. Let's build a new Google Colaboratory file. And now let's select here. Let me also zoom out for a bit. And let's select some stuff to then use in our script. Libraries and data for sure. So Control-Shift-S. And then let me just start selecting mounting the drive for sure. Okay, let me start again. Libraries and data, and then the drive, then the path also as well. Okay, I think I'm zooming out unintentionally. And then the libraries for sure. We'll also use all of them, loading the data for sure, but actually potentially not this loading the data. Let's use the other one. So this one where we use the index call, the parse dates, and so on. Resampling, don't care so much. Returns no data visualization. This one I like. So let me select. And then plotting, don't care so much. Data manipulation, we don't care. And seasonality, yeah, let's get it. Month plot, the quarter plot, yeah, why not? And then let me get the seasonal decomposition as well. And let's also get the autocorrelation and the partial autocorrelation. Let me do Control C. And now let me do Control V. Let's do step by step. Let's get rid of the outputs as well. We don't need them anymore. Because, yeah, this is just dummy code, so to speak. And this is going to basically be split currently in two parts. The first one, let me do just data frame and then replace here with dot head. The first part is on the libraries and data. And then the second part, which starts from the data visualization, I'm just going to call it here exploratory data analysis. This is where we become one with the data and really get to know our time series. And of course, we'll need to make some adjustments here and there. We'll also work upon this useful code template, and we'll keep on building, and we'll just improve it over time as we do this course. And this was just it. We'll use this in the future, but for now, I'm going to stop. Until next time, have fun. Have you ever been bombarded about stock price predictions? Well, then this video is for you. As we have seen, distinguishing between trend and seasonality in time series might seem straightforward, but why then is forecasting considered such a complex task? Why do organizations assemble dedicated teams for it? The challenge primarily lies in modeling and interpreting errors. It's about finding ways to explain these errors and incorporating relevant factors or regressors to improve predictions. What might these include? Consider diverse elements like specific events, temperature variations, snowfall, prevailing economic conditions, and even public sentiment. Each of these can profoundly influence forecasting accuracy. When it comes to relevance, the time horizon of the data is absolutely crucial. Let's say that we have data spanning 6 or 7 years. The question is, do we need all of it? Older data can introduce significant noise into our models. Why? Because past conditions may no longer reflect current or future scenarios. Thus, always assess whether your data is still representative of future trends. And if not, be wise to exclude it from your analysis. And then this connects us to our stock market prediction. We are constantly bombarded with articles claiming high returns using various approaches and algorithms. Remember, everyone is a genius in a bull market. But can these methods truly outperform professional investment firms? It's doubtful. For example, the price movements might suggest a trend, but it's incredibly challenging to predict when these trends will reverse. If there's no discerning pattern, traditional forecasting models struggle. This unpredictability was very evident when the COVID-19 pandemic struck in March 2020. The pandemic upended existing trends and seasonal patterns, rendering many forecasting models obsolete. It highlighted how external unprecedented events could drastically alter market dynamics. In summary, forecasting, especially in the context of stock data, is an intricate art that requires careful consideration of various factors, including the relevancy of the data, error modeling, and external influences. Until the next video, have fun. We have just finished the crossing line for this introduction to time series forecasting. Let's take a moment to look back and see what we have accomplished. It's been quite a ride, hasn't it? Think about where we started, just getting our heads around what time series data actually is. Now it's like we speak the language. We've gone from scratching our heads to nodding along as we analyze trends over time. We dove deep into Python, which was a game changer, wasn't it? We've moved past any initial intimidation that we might have, and now we really sliced and diced time series data like pros. Those Python libraries aren't just tools now, they are really something that you have on your toolkit. They are our partners in solving our time series data problems. And how about turning those raw numbers into stories? Our data visualization skills have come a long way. We're not just making any charts, we're telling stories that actually make sense to everyone. Remember grappling with the concepts of seasonality in our data? We've got a solid handle on that now. Whether it's spotting patterns in sales data or understanding seasonal trends, we've got it covered. Autocorrelation was another milestone. It's one thing to look at points individually, but understanding how they relate to each other over time, that's next level, and we're doing it. The big question about predicting stock prices, that was also an eye-opener. It taught us about the realities of forecasting and the complexities of financial markets. No magic crystal ball, but lots of smart, hard work. So give yourselves a huge round of applause. We have not just learned, we have applied, analyzed, and visualized. Until the next video, have fun. Hey everyone, and welcome. Today I'm going to talk about something pretty interesting. When forecasts don't quite hit the mark. You know, we all try to predict the future in one way or another, whether it's the stock market, fashion trends, or even just the weather. But sometimes things don't go as planned, and that's okay, because when our predictions go a bit sideways, that's when we really learn the most. So let's dive into some of the most memorable forecast fails and see what they can teach us. Number 1, the rise and fall of fidget spinners. First up, let's chat about these little spinning gadgets that took the world by storm a few years back. Fidget spinners. Remember those? They were everywhere. One day, nobody knew what they were, and the next, every kid in school, university, wherever, they had one. Retailers and manufacturers thought they had hit the jackpot. Production ramped up like crazy. But here's the kicker. The fad faded almost as fast as it started. Suddenly, stores found themselves stuck with piles of spinners nobody wanted. It was a classic case of mistaking a fleeting trend for a long-lasting one. The takeaway here? It's super important to ask ourselves, is this trend really here to stay, or is it just a passing craze? It shows the risk of jumping on the bandwagon without pausing to question the longevity of a trend. Next, let's talk about long-term capital management, or LTCM. These guys were like the rock stars of hedge fund world. They had this idea to use complex mathematical models to predict market movements. And for a while, it was like they had found the secret formula. They were making money hand over fist. But then, out of nowhere, the Russian financial crisis hit in 1998. And guess what? Those fancy models didn't see it coming. The market went haywire in ways LTCM's models couldn't handle, and the fund collapsed spectacularly. It was a harsh reminder that no matter how sophisticated our models are, there's always stuff they can't predict. the markets are a wild beast, and sometimes they throw curveballs that no algorithm can catch. Now let's talk about Google flu trends. This was Google's attempt to predict flu outbreaks using what people were searching for online. Sounds smart, right? They thought if more people were Googling flu symptoms, it probably meant a flu outbreak is happening. Initially, it seemed like a groundbreaking way to use big data for public health. But here's the twist, it didn't quite work out. Google flu trends ended up overestimating flu cases, sometimes way off the mark. Why? Well, it turns out that the how and why people search for things can change a lot. And as well, Google's search algorithms kept changing too. So, the lesson here, big data and fancy algorithms are powerful, but they can get things wrong if they don't adjust for changing human behavior and other factors. Last but not least, let's dive into the curious case of the Hindenburg omen. It's this complex technical indicator used to predict stock market crashes. It's named after the Hindenburg airship disaster. Pretty ominous, right? The idea is that certain market conditions, like the number of stocks hitting new highs or lows, can signal a big crash. But here's the catch. It's been hit and miss. Sometimes it signaled a crash that never happened, causing unnecessary panic. Other times it missed the mark completely. The Hindenburg omen shows that even the most complex and intriguing indicators can lead us astray if we rely too heavily on them without considering the bigger picture. So, what do all these stories of forecasting flops tell us? They remind us that the world is full of surprises, that no model, no matter how sophisticated, can predict everything. Whether it's a global health issue, the stock market, or the latest toy craze, there's always an element of the unknown. Welcome back. I am very excited to walk you through this world of exponential smoothing and Holt-Winters. In this video, we'll kick it off with the agenda that we'll cover throughout this section. I have a very fun case study lined up. Think of it as really the goal that we need to achieve. It's about customer complaints, and it's basically as real as it gets. We'll use this case study to apply our skills that we learn in a way that would completely mirror what you would encounter in the business world. Next up, let's talk about Python. So whether you're new or you are already friends with this programming language, we'll be using it, right? And this way, it's going to be how we get our hands-on experience. So please prepare yourself for some coding action as we'll go deep into it, really program everything that we need to do. Next up, we won't just stick to one type of exponential smoothing. Oh no, really? So we're going on simple, double, and triple methods. And yes, we'll put all of this with Python. So each smoothing method gets its own spotlight in our Python sessions. It's really where the magic happens, where the theory meets the practice. We need as well to learn how to measure error when it comes to time series forecasting. And as well, because data comes in all shapes and sizes, we need to understand how to do with weekly data, daily data. It's really trickier. So the more granular the data is, it becomes more complex, but we do need to learn it. And last but not least, we'll wrap up this section with a conversation on the pros and cons on exponential smoothing and Holt-Winters. It's always very important to understand what a technique can do and what it cannot do. So we're going to learn a lot, hopefully have some fun, and by the end, you'll have this Holt-Winters and exponential smoothing a topic dominated like a pro. Until next video, have fun. let me walk you through the case study for the section. So picture this, we have this challenge that we need to solve. Imagine that there is this company called TelecoWave, a very big player in the telecom world, and they're facing this real puzzle, this challenge. Their customer complaints are all over the place. Some weeks it's smooth sailing, other weeks really total chaos. And guess what? They've asked us to figure it out. So it's our job to predict these unpredictable swings. So why, you ask? So to help TelecoWave become better at customer service and to showcase how we can use data to actually solve this. So here's the problem statement. Telecom is really facing this issue, right? Because they get more and more complaints. They are literally scratching their heads over how many customer service reps they need for each week. So if you get it wrong, you're really wasting resources, which leads to unhappy customers. And this isn't just a numbers game, right? So you kind of need to bring order into this chaos. Therefore, we need to craft a strategy. So before we dive deep into any complex solution, we need to understand the basics. We need to get to know the data, what's behind these fluctuations, what are the hidden patterns that we may be missing. We need to dissect the whys behind these numbers. So we're talking about data analysis, right? So we need to explore the data. And this is really a big deal, right? Because if we nail this, this company, TelecoWave, can shift from playing catch, so either wasting resources or unhappy customers, and they can be in control. And by the end, the goal is to empower them to match their workforce perfectly with what the customers need. So fewer complaints kind of like fall through the cracks, and you have more satisfied customers and a healthier business. And this means more profits. Let's get it started. Until the next video, have fun. Welcome back. In this video, we'll start this practice journey into exponential smoothing and Holt-Winters. Please come to the folder of the course, which is the Python time series forecasting. And then let's start by opening this useful code because it has quite a bit of what we need. Plus, of course, we'll keep on building it throughout this course. Because, for instance, now we are going to deal with model assessment, more visualization, and all of this we kind of need to consider. That said, we have it here. And then let's go to time series analysis, and then to exponential smoothing here. And okay, let me double click again. Here we go. We have here 3 different CSV files. We are going to start to play around with the weekly customer complaints. And what I wanted to share with you, there's this, very short cheat sheet that you have here. And this is something that you can refer to. It's very important for the model assessment KPIs like the MAPE, MAPE, RMSE. We also talk about exponential smoothing and Holt-Winters. It's very, very short. It's kind of like this reminder that you can have, but it's here and it's here for you. Now, let me continue. Let me click here on New, More, and Google Collaboratory. And then in the useful code, I kind of want to select everything. And here we go. Actually, not really this one that I want to share with you, because that one I'm already working on. And let me go back. So let me see if it's this useful code template. Here we go. And could be this one as well, because it looks okayish, but already has here some functions that I built and that we will build as well. No, sorry. It's the useful code template. So let me select everything. So this is Control-Shift-S and then Control-Shift-A and then Control-C. And then let me come here and just do Control-V for everything. And let me keep here the useful code template as I'll add, but rather later in this section. And let's kick it off. So let me call it Exponential Smoothing and Holt-Winters. And in this video, we'll focus really just on the setup, and then we'll keep it going in the next ones. I want that it is very, very low key. Let's mount the Google Drive. So connecting and then connect to Google Drive. Here we go. Let me do Control Enter here. And yes, connect to Google Drive. So it's the same process, kind of. And yeah, let me get this account. And yeah, click on continue. And we are almost there. And here we go. Now we kind of need to get the drive here. But as soon as this is done. So mounted at the libraries, I'm not going to change anything for now. Of course, as we go through, I'll share with you the exponential smoothing functions and also how to measure the accuracy. And all of this needs to be added, but that is later on. Now, okay, so this has still not given me the drive, but here we go. Drive, my drive, and okay, I'm getting here a lot of videos, but let me get here now the time series analysis and then the exponential smoothing. Copy the path and then shift and then arrow and then Control V and then I set the directory. Now libraries, the same. Here instead of the Bitcoin price, it is the weekly customer complaints. Let me get it. Time series analysis, exponential smoothing. And here we go. Weekly customer complaints. So let me get this. And here we go. Weekly customer complaints. CSV. And okay, let me do Control Enter. See if it works. And yes, no, yes. Tiny error. Date not in list. If I go here, it's called week. No, that's important. And so index call week. Here we go. I need to Control Enter. And everything seems to be working because I have the complaints. Also, I have here some variables that we're not going to use for now, but we kind of have here the complaints. The week seems to be okay because it's 1st of Jan, then 8th, 15th. So everything seems to be a-okay here. One important thing is, okay, let's look at information about the data frame. That is dataframe.info. And here we go. We have that these other variables here that we're not going to use. They are integers, but discount rate and complaints are objects. Our focus for now is just on complaints. When it comes to exponential smoothing and Holt-Winters, you cannot really have extra variables. So the X, so these regressors, you cannot have them. So we'll just stick to complaints, which is an object. So this means that we need to focus here on some data processing. At the same time, let me add this one. So Control-Shift-S and then Control-C. And let me add it here because it feels important. Control-V, and here we have it. So that next time it's already there. That's it. I'm going to stop here. Next video, data preprocessing. Till then, have fun. Welcome back. Let's do this data pre-processing. Let me just briefly check in with the zoom. Okay, yeah, 125. That's more of our vibe. And now here, so what we need to do. Let's have a look here at our data frame and then complaints, because that is our main variable. And we have it here, it's an object. So that is the issue. And what we want here, and let's describe what we want. We want to transform it into a number. So either an integer or a float. Float, usually you cannot really go wrong with it. And at the same time, one of the things that's leading it to be an object, it's this comma here. So what we do is remove comma and transform into float. And this is exactly what we want to do. What we do is str.replace. Why replace? Because what happens is that we go there and we take the comma and we kind of replace it with absolutely nothing. So this is step one. Let's have a look. Here you go. You can see that the comma is gone. And what we do then is as a type, we go here and then float. Control Enter. And here you go. You can see that we have the dot and then the zeros. So this means that it is a float. I think for this case, because we're dealing with complaints, they should be integers, right? You could also go with int here, but float is also okay. It won't change anything. So what we do here is we then replace and transform our variable. So data frame complaints. Here you go. So this is what we do. Let's do data frame dot head so that we have a quick preview of what is happening. And here you go. This part here, we don't specifically care for now. Now, aside from this, let's focus a bit on the index. So data frame dot index. Let's have a look. You have here that we have week. It's a date time, so that part is set, but the frequency. So this is something that we can set as well. Now, let's give it a go, see what happens. One very simple way is that you take the data frame and then you do as frac. And one way is that you could include here the W. Let's have a go at it. Now, this is not working out. So, okay, what is wrong? What can we do? You can see here, if you notice that there's a mismatch, because here we have the 7th. And here we have the 1st and the 8th. So 7th and 14th. So something is wrong, right? There's a mismatch. What is happening? And I mean, let's have a look. So if we look at our calendar, let me put actually this date here. And let me do enter. Let's see what happens. And here we go. Okay, let me go and see if we can have a very nice preview. And here we go. So hopefully you can see. Let me do some zoom in. And here we go. You can see that the 7th is a Sunday. And what is happening, and this is what you can infer, and let me add it here as a comment. So setting frequency to W implies that the week starts on a Sunday. So you kind of need to know here is, okay, this data that we have that comes from this specific day, to which weekday it actually refers to. If it's a Sunday, this works. But in this case, it's not, because it's a Monday. And what you would do then is you go here to your W and you'd specify Mon for Monday. Control Enter. And here you go. So now it works. You could also do Tuesday. And of course, then it would not work out anymore. Let me do Control Enter. And here you go. So you set it to Monday, and this will definitely work. Let's go to our data frame equals to this. We transform it to a Monday, and let's fetch our index. Let me do Control Enter. So we have here frequency, weekly, Monday. And this is exactly it. Now we're done with the data pre-processing. Now let's go to the next step, which is really about changing a tiny bit the code that we have created and really get to know our data. Until the next video, have fun. Welcome back. Let's do this exploratory data analysis. We need to make some changes here. Let me add here, instead of close, we have complaints. Now, of course, you can really try to optimize this, but I'm also okay with making these tiny changes each time. One way is that you can just set the time series to a specific name, like Y, at the start, and then just have it, this code running each and every single time. Now, this is my view on it now. Doesn't mean that I won't change it later on, but for now, let's just stick to changing the variable name. Here, instead of daily closing price, would be weekly customer complaints. Let's have a quick preview to what is happening. Control Enter. And here you go. Let me zoom out here for a bit so that we have a clearer view. You can see that they are growing over time, right? You can also see that there are some spikes. And another thing is that these amplitude here, it's also growing over time. Not so much. It's a bit unclear whether the seasonality is additive or multiplicative. I lean towards multiplicative, but I couldn't say for sure. So I'll stick now with multiplicative, just so that we go ahead with it. But this is kind of something that you want to have a deeper look, especially as you model and see what gets the best result. That said, let's go here to our month plot. Now, this will be something that's not super helpful because we have weekly data. Here we go. Let's Control Enter. Here you go. Yes, while label complaints. Let me do Control Enter once more. We have the month plot. You can see that there's definitely some seasonality. You also see the amplitude. I would recall that these black lines, they refer to the values for each of the years. So this is where it starts in 2018. I think our data, it goes, so 261. Okay, you know what? Let me check. Let me do data frame dot tail. So this is one way that you can do it. And our data is done at the end of 2022. So 2018 to 2022, that's 5 years. And these refer, so these black lines, it's the 5 years of data for January, for February, and so on. And you can see that it grew quite spectacularly, with the exception of the last 1 year, where it kind of plateaued for almost every single month, with the exception of November and December, where it continued to increase. Next up, so quarter plot. Let me change here, complaints. And while label complaints as well. And let me do Control Enter. Let's have a look. So we also have some quarterly seasonality, right, with a peak in Q4. This is also something that we see with a monthly plot. And so it's Q2 and Q4, the high seasonality months. Q1, not so much. Then decomposition. And let me change here to complaints. Model multiplicative period, we do need to change, right? Because we have weekly data. How many weeks are per year? That's 52. And let's have a go. Let me do Control Enter. And let's see what the seasonal decomposition shows us. We have the trend, right? Growing over time, stabilizing. This is something that it is clear. Please also see that the first 6 and the last 6, they don't have a specific trend. They are outside of the scope per this function. And as well, if you look at seasonal, you see these spikes here. This is November, as we have seen. There's a spike in November. And you also see that, the whole Q4, there's a spike, and then it bottoms out twice. This is potentially Q1 and Q3, some periods around there. If we are to have a look here, so February and March, there's not a lot of complaints. Same thing with August and September. So 6. So it's 2 and 8, 3 and 9. So that you can also see that there's some kind of this seasonality every 6 months, which becomes clear. And this will be it. Residuals, nothing to notice here. Dot here and there, that's a bit outside. But aside from it, it looks very clear. Now, autocorrelation. Let's see how much information is in the past. Here we go. Let me do Control Enter. And you can see there's it really decreases over time. Let me change here the figure size here to 4. And here we go. Becomes much easier to see. You can see that it decreases, then it kind of increases. So this should be 6 months before. And then we have it here. And then there's a tiny spike, 52 weeks around that in the past. So this is also clear, right? You should have some kind of information that's 1 year before. But this definitely tells us that there is some information in the past to help us predict the future. And then the partial autocorrelation. So let's get rid of all these effects from the recent past for the correlations. And we see that the second and third week, definitely a lot of information. You also see this should be around 52, right? So 52 and 53, definitely a lot of information as well. So we kind of need to use this period of seasonality, right? So if you have a spike that's 52 times, so one whole period before, this tells us that we have a seasonal model. If we have information in the periods just before, this tells us that we should kind of use them to help us predict the future. And this was it. So as a recap, if we look at our data, there's a spike in Q4, specifically November, August, September, February, January. Not so much in terms of customer complaints. There is information in the past to help us predict the future. So this is clear here with evidence in 2 or 3 weeks before and also 1 year before. Now, let's learn some more concepts when it comes to time series forecasting. Till next video, have fun. Welcome back. Let me introduce you a very important topic in time series, which is splitting the data into a training and test set. Now, this is very simple and straightforward, but it's a very, very powerful concept. So imagine that you have this data set, which is represented by this blue rectangle. What you would usually do is that you would do this randomly split, leaving 80% for training and 20% for testing purposes. The key idea is to create a model using the training data and assess it with the test data. Therefore, you'd have this unbiased way of evaluating the model. Now, fairly simple, right? However, time series is a very different beast to tame because time series is different since one, information in a given day is meaningless if it does not have the context of the surrounding days, and number two, we usually want to predict the future. So if you imagine that this is our time series data, the practice of splitting time series is to remove the last periods. So for instance, in this case, I'm removing the last observation. Imagine this one is taken out. The yellow balls, they remain and become the training set, but they're not shuffled, right? So they are there still. And the light blue here becomes the test set. Another very important piece of information is that the test set should be the number of periods you expect the model to predict in practice. To explain it differently, if you are creating a model to predict the next 4 weeks, you should assess how it performs forecasting in periods of 4 weeks. If you do it for 3 months, you should test it in periods of 3 months. And last but not least, I want to mention that for the training data, you should have 2 whole periods. So if you are talking about weekly data, right, you need to have 2 whole years, ideally 3, so that you have very clear patterns. And the goal here is that you need to have data in order to achieve robust patterns, and which will lead then to robust forecasts. Now, let's see how this actually works in practice. Until next video, have fun. Welcome back. In this video, we are going to split the data into training and test. And as I have shared, right, when it comes to the test period, it should be very similar or equal even to what we want to predict. And let's say that our goal is to predict the next quarter. So that is 13 weeks, right? Because we have 52 weeks, so that's 26 weeks per half year. That's 13 weeks for each quarter. So 13 weeks. And therefore, if we do the training and test split, okay, let me go here a bit below, and let me zoom in as well to our 125%. Let's call it train and test. And what we do, so the first one is data frame dot illoc, so df dot illoc. For the train, I want everything but the last 13. So up to minus 13. And then I want everything. And then comma, and I do the exact same thing, data frame. And then dot illoc. Here I want starting from the minus 13, all the way up until the end, comma, and a 0. Now, let me set here periods equals to 13. And just before I do it, let me show you, right? So if I do this, and then let me check here my train, right? So we have all the way up until September 2022. And therefore, if I look at my test, I should have the whole Q4 for 2022, starting on October 3rd, ending up at 26th of December. So this is exactly what I want. Let me include here test.head. And so yeah, so test.head. I know that this worked, which is good. And then periods equals to 13. And then I replace here so that I just need to change the periods here once. This should be a bit easier when it comes to our testing. And that's it. So this was exactly what I wanted to do. We have split the model, and now we need to do some modeling. Let's kick it off in the next video. Until then, have fun. Let's talk about simple exponential smoothing. What's this all about? Imagine that you're checking our weekly sales figures or our weekly complaints. Some weeks are very busy, some weeks are not. We're trying to find a steady rhythm in these numbers, right? And that's exactly where simple exponential smoothing steps in. But it's not just doing an average, right? So it's like listening more to what happened to our most recent periods or our most recent sales. And this is represented in the formula. So let's break it down. The next forecast is a combination of the current level plus the alpha times the delta between the recent actual and the current level. Now, let me break it down for you. The current level, this is our baseline and our starting point. It's like saying, based on everything that we have seen so far in our data, this is where we stand. And then we have the recent actual. This is our latest observation, our most recent piece of actual data. It's like yesterday's numbers or last week's numbers. And then we have the alpha. This is the fine tuner, right? So when it's close to on, it means that we're putting a lot of stock into what just happened, and closer to zero, we're saying that the past matters more. Now let's put it into context. Say that our current level is 100 cups sold. So this is our baseline. But yesterday, we actually sold 120. Now let's imagine that alpha is 0.2. This will mean that our forecast doesn't jump to 120. Instead, it adjusts up a bit, acknowledging that we did better than our baseline, but not going all in based on 1 day's spike. So if we apply the formula with our current level being 100 plus 0.2, the alpha, and then 120 minus 100, this leads to 104. Now, the 100 and the 120, so these values are computed by the model. The alpha usually is selected, and we won't focus so much on selecting the alpha for now because the goal is to show you all this structure into time series forecasting. But if you were to go one level deeper, you could actually try to work with different alphas. But all this part on parameter tuning, we'll focus on it later on in the course. Now, let's apply it to our data. So if you look at our weekly sales data and we apply this smoothing, what we want to do is that we're trying to get past the spikes, like a day or a week when there was like this huge increase or a huge decrease. So this is very good if you want to have this broad stroke idea of where we're headed, like what we'll do with this exponential smoothing. Now, to wrap this up, while this method is a very solid tool in our forecasting toolkit, it's not a fortune teller, right? So it won't catch big trends or seasonal rushes. As we saw, the equation, it was, fairly simple. And as a result, we also have a simple outcome. And this is why it's also called simple exponential smoothing. It's a way to smooth out these spikes. It's a way to get these all chaotic numbers and simplify it. Now, let's see how this actually works in Python. And let's start building here from simple to double to triple. Until the next video, have fun. Welcome back. In this video, we'll focus on simple exponential smoothing. Exponential smoothing. It's very easy to put it into work. Let me show you. First, we need a function. And let me go back to our libraries here, and let me import some stuff from stats models dot tsa and then dot Holt-Winters. What we do is that import the simple and then exponential. So simple exp smoothing. So this one. Let me do Control Enter and let's go back, scroll all the way, and let me show you. So let me add here as our comment. So simple exponential smoothing model and prediction. So let me do it all, not in one go, but in a couple of lines. The way that we build the model, let me call it model simple. We use the simple exponential smoothing function. And inside, I include my training data. And then I use the fit method here. So model built. Really easy, right? And then what we would do if we want to make the predictions, we take the model and we use the forecast method. And what you need to include here is how long, and even see here steps. So how long do we want to make the predictions? Now let's standardize this. We do length of test. And now let me do Control Enter. And as you can see here, like all the forecasts, they have the same value. And this is expected. Each time that you use the simple exponential model, you will get the same value for the forecasts. And that is because the way that the formula works. Because the recent level will always be the same, the current level always be the same, the alpha is always the same. Therefore, this means that we always have the same forecast. Now, we're just getting started, so what we see here is the same, but as we go to simple, or better yet, as we go to double and to triple, then this changes. Now, let me store this, because now what I want to do is I want to build a structure where we build a model, we train the model, and we predict, and then we visualize, because visualization is very, very important. Let me store it under predictions simple. Here we go, equals to this. Let me do Shift Enter. And now what I want to do is to plot. And what do I want to plot? I want to plot my training, test, and forecasts. And this is what I want to show you. Let me start by building a very simple visualization, and then let's build from there. So plt.plot, and I include my train. So this would be the initial starting point. It's thinking. And then if we have here the dots show, this is always the end goal here. And then we can actually build some more. Taking quite a bit of time to think, but let's keep it going. plt.plot. Here I put the test, and plt.plot, I include my predictions. Simple. Control Enter. And here you go. Here you can see the actual values and the predictions. Horrible result, right? But that's not the point. We'll improve. But it's important to have this in mind, right? So this is terrible. And let's see how we can go from there. That said, let's focus here on what is the predictions. And let's start by adding here some labels. So label equals to train. Label equals to test. And then here label equals to And then I put here my predictions. No, forecast. I prefer forecast. Now, if I do this, let me do Control Enter. And getting an error, got an expected keyword argument label. So let me correct that to label. Control Enter. And here you go. You can see that we don't have it, right? So where are my labels? And the thing is that we need to do plt.legend. Here we go. Control Enter. And we should see it here on the left. And as you can see, I'm like going up and down, up and down. So let's go here and do plt.figure. And then we set the fig size equals to 10 and 4. Here we go. So this should be better to visualize. Also, we have some time series data here, which is quite long in time. So it's also very helpful that we have our chart with some higher width. And last but not least, let's add some title. So plt.title, and then here what we do is, train, test, and predictions with simple exponential smoothing. And let me do Control Enter. And this is our chart absolutely done. Conclusion, horrible. Now, I'm not even assessing the model as of this moment, right? We can just immediately notice it's horrible. We have a more structured way of assessing the model later on in this section. But before we get there, let me show you some more exponential smoothing. Next up, double. Until then, have fun. Let's dive into double exponential smoothing. And you can see here with our 2 stars. And one question you might have is, what makes it double? In simple exponential smoothing, we focused on smoothing out the data. Double exponential smoothing adds another layer. It tackles trend in our data too. So we're not just averaging out the highs and lows, we're also catching if our sales are generally going up or down over time. So if we break down the formula, double exponential smoothing is essentially 2 equations. We have the smoothing the level, which is the equation that we saw before. It's very similar to this one. This one is transformed, so to speak, but it's the same. And what we add is that we also smooth the trend. And therefore, we also have a different element because now we have this beta. So let's have a go at it. So we have the smooth level. This is our updated baseline, which takes into account the recent actual data. We have the smooth trend. Here, we're looking at how much the level has changed from one period to the next. It's the trend factor. And then we have alpha and beta. And these are our levers again, right? So alpha adjusts how much we consider the recent sales versus our previous level and trend, of course. And beta tunes how much weight we give to the change in trend. So basically, how quickly we think the trend change is happening. Now, let's put it into practice with an example. Let's say that our sales have been increasing overall, but with some weekly ups and downs. Double exponential smoothing helps us to see if that upward trajectory is actually coming from the trend and not just from these weekly fluctuations. And as before, some words of caution. While it's absolutely great for catching trends, we are still not handling seasonality. And this is something that we'll work on with triple exponential smoothing. And that would be a wrap here. Double exponential smoothing smooths out the noise in the current values that we have and also the trend. It's all about understanding if we can catch the wave or not. And it understands or helps us understand where or in which direction our sales are heading. And that's enough for now. Let's see how to actually make this work in Python. Until then, have fun. Welcome back. Let's focus on double exponential smoothing. We need a function for this. And so double exponential smoothing. And this function for a double, it's also the same for triple. So we won't need to worry about that in the next practice video. It's called exponential smoothing. Exponential smoothing. Let me do Shift Enter. And coming back all the way to the bottom, let's see how this works. So we need to do our double exponential smoothing model. Here we go. Let's call it model double, and then equals to. So equals to, and then we get our exponential smoothing. Okay, am I writing it correctly? Yes, I think so. Anyway, now we have here the train. So this is our data. And then let me see if I can get here some help. Let's see what comes out. Oof, I love when you have like nice documentation. What I want to show you. We have here the trend. And so far we have talked about the seasonality being additive or multiplicative, but this also happens for the trend. So trend can also be additive or multiplicative. How would it work? It would work here in the same way because we have the current level and that is the value. And then we have, or we would look at it here at the trend. We would see, okay, is it growing a lot over time or not? Or is it kind of stable? Is it linear or non-linear? And here for trend, usually additive is the way to go. Additive. You can try both. That's for sure. See which one has better results. But so far, let me do additive and then show you multiplicative as well as we do the visualization. And as well, we would have here the seasonal periods, but that's not for now. Therefore, here our seasonal component here, this will be none. And this is what sets the difference between our double and triple, is that we include here none. And then we just do dot fit. This would be it. Let me do Shift Enter. And okay, invalid syntax. Perhaps you forgot a comma. Oh, this is a very good error, right? Because it's kind of telling you that we're missing something. And that missing is a comma. Here you go. Control Enter. And oops, got an expected keyword argument, trend. Okay, that's fair. Let me correct it. And yes, 3 times the time. Now we focus on predictions. So predictions. And the way to go, and let me just copy this. So Control C and Control V, predictions double. We use the model double. And then it's the same. So the forecast remains the same. Now, we could just do this. And let's get here this code. So Control A and Control C. And Control V now. And then the train remains the same. So train and test. And then we have predictions double. And let's go. And let's do Control Enter. Now, you could look at it and say, okay, Diogo, before it was a normal line, just, horizontal. Now it's again, I thought you said that, for double, it was different. And the thing is that it's horizontal, but it only kind of looks like it. So if I go to our predictions double, it's rather a coincidence that's horizontal because it's not the same, right? It's slightly decreasing over time. So this is the current trend. And if we go and we have a look at our seasonal decomposition, I don't know if you saw, right? But it's kind of like stabilizing. And according here to our double exponential smoothing, now currently it's decreasing over time. So this is our general assessment as of now. That's it. And as promised, let me show you. So multiplicative, you can also just include MUL for multiplicative. This works. It immediately gives us an error. It says that convergence warning, optimization failed to converge. This means that when it comes to fitting this type of model with multiplicative trend, it did not work out well. It means that the errors are way too high and that we should not use it. So, but it's just a warning, right? You can still use it. That is okay. So if you go and we have a look at it, you can see that it's slightly going up. The difference is not so much, but the model is just telling us, yeah, this does not seem to work out so well. But again, we focused on results. And if I were to just look at the two lines, I would say both horrible, but one or this one, which is multiplicative, a little less horrible. That said, right, one of the things that we discovered in our exploratory data analysis is that we have a very deep seasonal component here. And this is what we need to focus on. And that is also the goal of triple exponential smoothing. Till the next video, have fun. Let's talk about triple exponential smoothing, which is often referred as the Holt-Winters method. This is like a big sibling of the simple and double exponential smoothing that we have just discussed. It's designed for data that has not just trends, but also seasonality. So think about our patterns that we have seen, for instance, our data of customer complaints. It has a deep seasonal cycle. And this is important to reflect. And how does it work with this, triple exponential smoothing? Our data is split into three components. The first one is the level. This is what we saw in the simple exponential smoothing. It's about the baseline value of our data. Then we have the trend. Here we're looking at whether our data shows an increasing or decreasing trend over time. And then lastly, we would now have the seasonality, right? So trend was double, and then with triple, we have level, trend, and seasonality. And these are the repeating patterns over time. So how does it work? The Holt-Winters method uses three equations, each corresponding to the level, trends, and seasonality. Now, I'm not going to go over the equations because we did it for the simple and the double. And now it's just a tiny bit too complex because it's quite a bit of equations and how they work with each other. But let me give you the gist of it, right? Let me give you an overview. It starts by adjusting the level. So first it does the simple exponential smoothing. Then it looks at the trend and sees how this average over time has changed. So this is the beta component. And lastly, we have this seasonality, right? So after the level, after the trend, what is also there to be considered is the repeating cycles over time. And just like in previous methods, we also use coefficients. So we have alpha, beta, and gamma to control how much weight we give to each component. With alpha, and beta controlling the level and the trend, as we saw before. And now we have gamma, which controls the seasonality. If we were to put this into practice, we would tune these parameters. We won't go there just yet. This will wait until we do the SARIMAX. This is where we'll go into parameter tuning. For now, we'll focus on understanding how this works. And then, of course, you can come back with the knowledge of parameter tuning and try to apply it here. But for now, even though that is the natural next step, we are currently focusing on learning the basics of time series forecasting. And last but not least, in terms of practical applications, it's very important that we have a seasonal curve, right? So this is an extra layer of complexity. And for instance, when we do EDA, so exploratory data analysis, and we see those deep seasonal curves, you kind of need to use Holt-Winters, right? So double exponential smoothing won't work like we saw, right? The results were not good. And for instance, other examples would be if you want to predict electricity demand, which has daily or seasonal patterns, forecasting retail sales that spike during the holidays, you kind of need to have a model that takes into account seasonal fluctuations. And to conclude, Holt-Winters is a robust tool for dealing with complex patterns in time series data, and it helps us to forecast more accurately by considering not just the trend, but also the cyclical nature of our data. Now, let's apply and let's see how easy it is. Until next video, have fun. Welcome back. In this video, we are going to cover triple exponential smoothing, and this is a lot like repeating the double exponential smoothing, as you'll be able to see. This is also known as the Holt-Winters method. Why it's called Holt-Winters? Because it was developed by someone named Holt and their student named Winters. Yep, not kidding. This is actually true. So triple exponential. Now, I'm just going to copy what is above because from a complexity perspective, Holt-Winters is more complex. But if I look at it from a programming perspective, it's almost the same. So let me do Control-Shift-S here to select, and then Control and select. Let me do Control-C. And for some reason, I'm having these squiggly lines, which says that there's an error. But when we get there, we get there. Now, let's replace what needs to be replaced. So model triple and triple exponential smoothing model. We still have the train. Let's change the trend component here to additive because there was an error before. Now, seasonal, this one, we can specify what type. And let me include here multiplicative because even though it's not super clear, but it does feel like the amplitude over time increase. And therefore, this would mean that we have multiplicative seasonality. So let me put it here. And then what we also want to include is the seasonal periods. So here we go and we specify 52 because we have 52 weeks per year. Now, let me do Shift Enter. Okay, everything is working. Here will be predictions triple. We also use the model triple. And we can have a quick preview here. Let me do Control Enter. And here we go. We see it here. You can also see that it fluctuates quite a bit. So now if I go and I plot, I need to change here the predictions to triple. And so with triple. And if I have simple here, then it also means that I did not add here double. So let me correct that. We do Control Enter here in the double so that we replace the title. And now here in the last piece, we have our predictions. And you can see it works really well. Or apparently it works really well. Because there's a very, clear adherence between the test and the forecast. And as a result, when it comes to these seasonal fluctuations, what we were seeing above, the real issue is that we did not have these seasonal cycles in the model. And this was something that we needed. Now, this is a visual inspection of the outcome, right? It's still a bit difficult to say in terms of a metric perspective, how far away are we? And this is what I want to cover now. So in the next video, I'm going to show you about the 3 main error metrics that we use in time series forecasting. Soon after, then we're going to do it with Python. Until the next video, have fun. Okay, let's talk about how to measure accuracy errors in time series forecasting problems. Now, I'll admit, this is not the most interesting of topics, but it is very, very relevant. So let's go through it. The way that measuring errors in regression or time series forecasting is always the same. You have a model, which is represented by this line, and then you have the values that actually happened. And we have different ways of measuring the error, which is always the delta between the actual values and the line, right? So the delta between what actually happened and the predictions. Now, there are multiple ways of measuring this distance, and this is what I want to cover. There are 2 very big KPIs here that I'll talk about first. The first one being the mean absolute error, the second one being the root mean squared error. The formula for the first one is the delta, which is a simple subtraction between what actually happened and the prediction. But with a key difference is that we have this absolute, which is represented by the vertical lines. We do this sum of the absolute differences. In other words, this is the average delta of the absolute differences. Now, I will briefly go through this, but just in a little bit, let me show you the formula for the other one, for the root mean squared error. And this is the delta, also a subtraction between both, but then you square it. This square also makes it positive. So this is the average or the root average of the squared differences. Now, the most important thing to have here in mind is what does this actually mean? So, of course, aside from measuring and understanding error, there are pros and cons to using either or. The mean absolute error, so as I've shared, is the absolute or the mean of the absolute differences. But this absolute component makes it very important so that you don't really negate or cancel errors. So let me give you an example. If one error is 100 and the other one is minus 100, the mean error would be 0, right? Because 100 negates the minus 100. But the mean absolute error would still be 100. The root squared mean error, this one is the root mean of the squared differences. And it's not super interpretable because as soon as you start squaring and applying the root square, you kind of lose this interpretability, but it's very useful for handling outliers. So what is happening is that even though the mean absolute error is more interpretable because mean absolute difference of 2 does imply an average of 2, but the root mean squared error does not tell us that. But it does punish outliers, right? So extreme differences do get punished. So when we see and we look at the root mean squared error, this is a KPI that we use when we have some extreme values and you kind of want to punish those errors. So that's very important. In general, we kind of use both. So we'll use both and have them. But if we want to have one KPI that we use in order to fine-tune the model to say this model is best, it will be the root squared mean error. Now, there's a third KPI, and there was a tiny spoiler just before with a MAPE. And the MAPE is with this formula. And it is the average absolute percentage delta. And what does this mean for us? The MAPE is very interpretable because the error metric that comes out of it is a percentage. However, and this is an issue, it gives the same weight to all observations. So if the prediction is 100 and the error is 10, the MAPE is 10%. But if the prediction is 10, the error is 1, the MAPE is also 10%. And with the other two KPIs, this does not happen. I would posit, so I would say that predicting the 100 and getting it right is more important than predicting the 10. So we don't have this punishment for the MAPE, but for the mean absolute error and for the root mean squared error, there is that punishment. And that's important because with a MAPE, you kind of have the same value for both, but in practice, that's not really the case. Following on this, there's one question that I get asked all the time: what's the ideal error? And the truth is that there's not an ideal error. The ideal error depends on the situation and what is like your leeway, how much error you can actually have. And the important thing is that you kind of improve over time. So you use better models, use better data, you just improve the way that your time series forecasting actually works. To sum it up, mean absolute error is an average of the absolute differences between the actual and the predicted values. The root mean squared error is the root average of the squared differences between actual and predicted values. And the MAPE is the average error in percentage. And lastly, when it comes to the ideal error, it depends on the problem. Discuss it with your stakeholders, your senior managers, see what you can have, because it's impossible to say. There's no standard to say what is the ideal error. And now let me show you how to compute them with Python. Until the next video, have fun. Welcome back. In this video, I'll show you how to do the MAE, the MAPE, and the RMSE. And let's go here through our table of contents. And in this part here, let's add the last one. So we import from sklearn.metrics. So sklearn.metrics, we import the mean absolute error, the mean squared error, and it is with this mean squared error that we do the root mean squared error. And then last but not least, the mean absolute percentage error, or MAPE. Let me do Control Enter, and here we go. And we have this here, and now I return all the way to the bottom, and let's do it. And we start by calculating the MAE, RMSE, and MAPE. And to do it, let me store them here, and then we'll use the print function in order to retrieve these outputs. We start off with the mean absolute error. And inside, and this is the same for all, but let me show you for one. What we do here is that we have the Y true and the Y pred. The Y true is what actually happened. So for us is the test. And the Y pred is our prediction. So for us, it is our predictions triple. Here we go. Predictions triple. Now, if I just do this, here you go. We see that the MAE is 366. And I kind of want to print it here. So print with an F string, the MAE is, and then curly brackets, MAE. So this is in general enough. You can kind of as well, because you have a lot of decimal cases, so you just do colon dot two floating points, Control Enter, and here you go. I think this looks much better. Now let's repeat this for the remaining ones. Now here I'm going to copy paste because there's no reason why we should not take the path of least resistance, right? So the easiest one. So mean squared error. And the thing is that, let me put here, what we want in the end is the root mean squared error. And what we would miss, and let me actually show it to you. So print with an F string, the RMSE is, and with some curly brackets, RMSE again with two floating decimal cases, right? We have such a big value. That is because this mean squared error is without a root. And what we need to do here is squared. And let me show it to you in the documentation. Squared. So if true returns the MSE and the default is true. And if false returns the RMSE. So what we want here is in the end squared equals to false. Control Enter. And here we have it. And then last but not least, MAPE, mean absolute percentage error. Again, the test and the predictions triple. Here we go. And then here we repeat the process with an F string, the MAPE, and then is. Now let's see what comes out. We started like this. We see 0.08, and this is great. But the thing is that this is not in percentage, right? So this is not 0.08%. So what we do here is that we multiply this by 100. Here we go. And this is something. Now, let me do dot. Let's start with 2F. See what happens. And I'm getting an error. So let me change here the 100 to the beginning. And I do like this. Let me do Control Enter. Here we go. 8.52. And now outside of the curly brackets, I add percentage. And here you go. Much better. So overall, we definitely get some good outcomes. I would say 8% for a weekly forecast over a period of a whole quarter. So 13 seems pretty convincing to me. And the thing is that we don't really have a baseline here, right? So what are we improving from? So that is not clear. But because the goal is always to improve over time. But let's say that this is our starting point, and then you kind of want to build from there. You want to try different versions of the model. You want to try different models, and you want to improve versus this 8.5 or this 366. Now, let me kind of bring everything together, and I would ask that if you want, you can stop here, but I want a function to assess model and visualize output, which is in a sense combining what is here and what is here. So please pause here, give it a go, and I'll see you in a few seconds. All right, did you do it? How easy was it? Super difficult? Okay, let's give it a go. So define model assessment. And in this model assessment, we kind of need to think of everything that we have included. We include a train, a test, predictions, and as well a title. So this is also something that we kind of need to include here. So a train, a test, predictions here, and the chart title. And then colon, and now let's bring. So what do you think? So first the errors and then the visualization, or first the visualization and then the error metrics? What do you think? Okay, let's start here with the visualization first, and then we can iterate, right? This doesn't mean that this is set in stone. And let me do a tab here. Now let me change here, because let me give it, or it's better to always give it a name that's not, too specific. So predictions. And at the same time, of course, it's important that it's the same name as the input so that it's easier here to do. Now, what I want here is for the title, right? So it's an F string with, and then here I'll just put chart and then title. Here we go. Then we would continue, right? And then we do this part of calculating the stuff. And let me do, okay, did not copy well. Control A, Control C. We try again, Control V. Selecting everything, a tab. And let me replace, right? So predictions all the time. And here we go. Now let me do Control Enter. So I know that this works. And what I kind of want to do is, so let me take this, let me put it here. And let me show you around, right? So we have our train, our test, our predictions, triple, right? So this is our name. And then our chart title would be Holt-Winters. Let me give it a go. So Control Enter. So I know that this works. We have here our MAE as well. And this is also working. So this is great. And then let me just show you something. So because we have such a long data, right? So we have so many years. You can also just go here and do, okay, from 2023 and then onward. And let me do Control Enter. And here we go. So, or better yet, not 2023, right? But 2022. And we just have this part. So this last year and how the predictions and the test are connected. So this helps. You can also say, hey, you know what, from June 2022. And that's also okay. You can also visualize it like that. Just to show you that we have this function and we can definitely play around with it. In the next video, we are going to cover the very important topic of predicting the future. Here we go. And yeah, until next video, have fun. Welcome back. In this video, I'm going to show you how to predict the future using Holt-Winters. And I'm going to do mostly copy pasting because we have built basically everything. Now it's really about tailoring. And this happens. So you do your training and test, and then you say, yeah, you know what? This model is kind of good. We can definitely use it. Then you want to make some predictions. And let me go here. We kind of want first to get this model building. We want to make some predictions, and we want to make some visualizations. And we don't want to measure the error, right? Because you cannot really measure the error when you apply the model, when you're predicting the future. You can measure it afterwards. So as you make the predictions, and then you compare the predictions with what happened. But that is in the future. Currently, it's basically, yeah, let's use it to predict the future, and let's apply it. This is how you put a time series forecasting model into production. Now let's change here And let's see what requires change. So instead of the model triple, let's call it model final here, or just model. That also works. Instead of train, you put the whole data. And this is important. So data frame dot complaints. Let me also add it here to predict the, or not here, because I may go too much to the right, to predict the future. You include the whole data as training data. And this is why we include our data frame dot complaints. Now, the remaining part is the same. So it's the same model components that you have done. Let me do Shift Enter. And then here, let's call it forecast so that we also have something that changes. And just so that it's not confusing, here you specify how long. So let me put 13 periods. And I use the model. And then let's have a look at our forecast. Control Enter. And here you go. So you see here that we are now going to 2023 with our forecast. And then for plotting, so plot training and forecast. And this is what we include. So instead of train is our data frame dot complaints. And we no longer have a test, right? Because everything goes inside the data frame dot complaints. And then we have our forecast, and then title, train, train and forecast, and forecast with triple exponential smoothing. So this works. We have done our predictions. So now let me do Control Enter, and this is how it works, right? So this is how we see the current level of forecast for 2023. And again, because we don't really have data to compare, at least right now, what is happening is that we just have this orange line here. And this is how many complaints we expect to have in the next 13 weeks. Now, let me build here a function, because this can be helpful in the future. Here we go. So define, and I'm going to call it plot future. And this one here, it includes a Y, right? So it includes a time series. It includes a forecast, and it includes a title. And here, let me do a colon, right? And now, instead of data frame dot complaints, a Y, forecast remains the same. And then train and forecast with, and let me put here the title. And this is actually it. Let me just do Control Enter. No. I'm doing something wrong. I'm missing here an F string. So let me do Shift Enter. Now, yes, everything seems to be correct. And let me actually put it here. Data frame dot complaints, and then the title. Yeah, let me put title. Why not? I just want to make sure that our function is working well. Yeah, it's working well. So this is perfect. And let me add here as a comment. So function to plot the future. Now I'm going to stop here. And this is kind of the end of our case study, because we have, in a sense, predicted the future. We have done our model. And now let me show you how to do it with daily data, because As I think I've shared, the more granular the data, the more complex it can be. So I want to show you around. I want to show you how this actually works with Bitcoin data and with Holt-Winters. Till the next video, have fun. Welcome back. Let's now focus on daily data. Here we go. And what I will do is that I'll take our code and I'll copy some of the stuff that we have done so that we maximize what we have done so far. I'm going to start here with loading the data. That was the first step. So I'm going to do Control-Shift-S. And then information, this is always good. Data, preprocessing, I don't think we need. But the frequency, this is always relevant. So I'm going to take all of this all the way up until the end. Here we go. I'm going to put it here. Control V, but it's not. Okay, I have no clue what I'm copying, but it's not the right thing. Okay, let's try again. So let me go here to our loading the data. So Control-Shift-S, and let me get these two for now. And let me go to our daily data. And so this is part one. And then the other thing was about the frequency. And we'll start there. And here you go. And let me put it here. Now I'm going to call it data frame daily. And I'm going to get our Bitcoin price. And here you go. Let me put it here. And let's go step by step. So data frame daily here as well. And let me do Control Enter. Getting an error. Week is not in list. Let me go to our Bitcoin price. The name of the date column is called date. Okay. This is very easy then. With a capital D, right? So let me do Control Enter once more. And here we go. Also seems to be correct. So 17, 18, 19, so on. Seems to be okay. Let me get the information about the data frame. Okay, but not this one. The daily one, Control Enter. And float. And now the frequency. Let me start by examining the index. And here you go. Daily, Control Enter. And we have daytime, frequency none. Now let me change here to day. And let me do Control Enter. Frequency daily. So also easy for us. Now, it's always good to do some kind of training and test, and that's actually our goal here. So training and test, and then let me do the triple exponential smoothing, so Holt-Winters. Now, let me go here, and let's make the changes. So train and test split, like let's say 30, because there's 30 days. You can also just keep 7. That's also okay if you want to predict a week. It really depends what is your desired forecasting horizon. Now, I kind of need to replace the inputs to data frame underscore daily. And at the same time, I want the close. So I have here a 0, right? So let me do 0, 1, 2, 3. I can either get the 3 or the 4, it doesn't matter. So 0, 1, 2, and 3. And here I'll get 3 and 3. So this is enough. Let me do Shift Enter. And then I have my model. So this works. Not going to make, sorry. I need to make this changes. So 7. And let's have a look here as well. I don't think we went really deep into the seasonal periods. So let me try to see and get it. Here we go. So seasonal periods, the number of periods in a complete seasonal cycle. So 4 for quarterly or 7 for daily with a weekly cycle. So we put 7 here. Let me do Control Enter. And okay, so let me have a look. No frequency information was provided. So inferred frequency D will be used, which is okay, right? It's telling me that there was, okay, here was the issue, right? Should have been our daily. Here you go. So this is on me. So it was my error here. Let me try again. And now we do have this convergence warning. Let me put additive into 2. So, okay, so also not working. Multiplicative. Okay, also not working. Like it can also happen and that the model is just saying, hey, you know what, this trend seasonal is not really working out, which is fair, right? It can happen. This is when you'd usually try a different model or assess. But for now, we'll just keep it like this, right? Convergence warning. We will need to move on with our lives. And then we make our predictions. Here we have them. And now let me go and get here. So not the goal, but what I want our functions, right? And we had this very nice function on model assessment. And going back to our daily data, and at the very end, when you really have these functions that can help with your life, just makes it easier and far more efficient. So model assessment. Let me take out here this train. We have the test, the predictions triple, and then we have Holt-Winters. Okay, let me change here to Holt-Winters versus Bitcoin. Control Enter. And let's visualize here as well. We have a lot of data, right? So let's focus on 2023 onward. Let's see if that is enough. So it kind of works, right? You can see that there's a very steep trend. Holt-Winters can recognize it. The seasonal cycles, we cannot say that they're there, but let me have a look from 2023 and November. So this allows us to zoom in. Seasonal cycles, they're not really there. And then we see that there's a bit of a miss. If you look at the MAPE, so 5%, kind of okay, but also not okay, right? If you miss by 5% when the market on average grows 8%, it's a big miss all the time. But that said, right? When you have the daily data and the goal was to show you this seasonal periods equals to 7, and everything else kind of remains the same. And we have this function now that helps us to perform better, to do it faster. And I think that's a good thing. Now I'm going to stop here, and in the next video, we'll tidy everything up with our useful code template. We'll put our functions there. Till the next video, have fun. Welcome back. From our exponential smoothing script, there's a few things that I want. Let me start with the libraries. And here, what I really want are the metrics, because it's those that tell me whether our model is good or bad. So let me get those. And then we have exploratory data analysis. Let me add here model assessment. So this is one, and then the other would be predicting the future. Predicting the future. For now, we just have plot the future. That is because most of the times what we have is that each model has its own way of predicting. So it's a bit difficult to standardize. But for now, let me get the functions. So I found a plot the future, Control A and Control C. I'm going to put it here. And then the other one was the model assessment. And it's these two that I want. And then we could also take the training and test, but a lot of times there's some functions that are very specific. So for instance, we'll also move on to do some cross-validation, which will be important for us. And as a result, this training and test split won't be so used. That said, this is it. And you can kind of see that we're starting to build. It's there. And in general, right, you kind of see that we have the data, we explore the data, and then we'll have some part of modeling. And then for model assessment and predicting the future, and in this case, we just have the plot. For the data visualization, we're doing very, very well. And now it's really about building on top of what we have. And with this, I'm going to stop with this practice activities into Holt-Winters. I hope you had some fun. I for sure had. I would love to hear your feedback on this section. And otherwise, I'll see you in the next video. Hey everyone, in this video, I'm going to walk you through the pros and cons of Holt-Winters method, breaking it down into key advantages and also its limitations. As a general introduction, so Holt-Winters is a favorite in the forecasting world, right? So if you have a not so complex problem with trend and seasonality, Holt-Winters does a very good job. And that's really its first advantage, right? It's a very, very simple implementation. It's straightforward. You don't need a PhD to get it up and running, which makes it accessible for many. As well, I find it quite intuitive. So the model's logic, which revolves around the current level, the trend, the seasonality, it really resonates intuitively. And the parameters that we talked about, and in fact, we didn't really need to go deep into this alpha, beta, and gamma, right? So they're there, they exist, but for this very easy implementation, we didn't even work with them. As well, it is adaptable to changes. So again, these parameters and the way that the model works, which is the information in the recent past, that's the most important in order to predict the future. It makes the model very adaptable because it takes the most information from the recent past. When it comes to the limitations, it just has one seasonal component, right? So for our daily data, we kind of had to pick for weekly or for yearly seasonality. But why not both, right? Most of the times we do have both. And this does not allow us to have that in mind. It's an issue with these older methods. With the ARIMA family of models, it will be the same. These models struggle when we have complex time series. And then as well, speaking of complexity, we don't have room for regressors. So the external factors cannot be used to refine the forecasts. Holt-Winters does not have that flexibility, and it relies 100% on the historical data of the time series, which is not always the case, right? What about the weather? What about the investments? What if you want to include COVID, right? All this external stuff you cannot include. And therefore, Holt-Winters is very good for simple problems. But then when you have something that's more complex, then it fails a bit. Last but not least, let's conclude. So Holt-Winters does stand out as a reliable method because you can just put it there up and running, really, just try it out and see how difficult it is to predict. But it's also important to recognize that it may not be always a perfect fit when we have multiple seasonalities or when external factors play an important role. I'm going to stop here. It's time that we go to our next section. Until next video, have fun. Hey everyone, and welcome to this challenge. In this video, I'll present it to you, and hopefully you will be able to solve it alone. And otherwise, in the next video, I'll solve it with you. Here we have the Capstone project, and you have the instructions and the dataset. This here with the challenge, this is the bare minimum, right? You kind of need to work with the data frequency, visualize the data, training and test set, build the Holt-Winters model, forecasting, and the accuracy assessment. So this is absolutely the bare minimum. You're welcome to do more. And my one advice to you is that you use the useful code template as much as possible. Work with it and see how you can actually now apply this to a whole new challenge. Now, I'm going to stop here. This should be easy challenge, should not be super complex because we have practiced a lot. And with this, I'll stop now and I'll see you in the next video. Welcome back. Let me solve now the challenge with you. Let me click on New and then More and then Google a collaboratory file. I would also ask that you share with me your feedback on this. Was it difficult? Was it easy? I'll be very keen on knowing how you performed. That said, let me start here and let me zoom in. So 125. That's more of our jam here. And let me add, so Capstone project. And it is air mass. And in our data here, we have a CSV file and we have the amount of air miles per month since 1996 all the way to 2005. This is a classical time series forecasting problem and also dataset. I'm sure that you can actually find quite a few examples with this dataset because it's very well known, because it's very good to kick it off, especially with Holt-Winters to study the seasonality. And this is why I also chose it here, so that it's a very nice introduction, or at least I feel that way. Now, in the useful code, let me get everything. So I'm going to select. Okay, it was basically dragging itself. Control-Shift-S, Control-Shift-A, and then Control-C to copy everything. And let's do it step by step. And let me start by mounting the Google Drive. And here we go, connect to Google Drive. And then, I'll just do it step by step. And then another thing, I was looking at it, and the more I think about it, the more I think that we should change here from close to Y, so that it is something that's more agnostic, so something that can be used again and again. And therefore, I'm going to do it now. So I'm going to select, I'm going to go to find and replace. And then I'm going to change here from close to Y. And I'm going to replace in all instances. Now, of course, the title is something that needs to be changed as well. But for now, at least, I'm going to leave it like this. And this is something that's easier to do. In the meantime, we have this here. And it's not mounted yet. Okay, let me reload this page because sometimes that is helpful here. And then we can kick it off. And okay, connecting to a runtime again. We have here the drive. So my drive, Python time series forecasting, and then time series analysis, Capstone project. Go to the 3 dots, copy the path. And let me come here, Control V. And let me get more space and Shift Enter so that this works. We have the libraries and we kind of need more libraries here, or, specifically we need something related to the exponential smoothing. So I go and I do from and then stats models dot and then here TSA and then dot Holt-Winters. I import the exponential smoothing. Here we go, Shift Enter. And the data set, and here you go. So the data set is called air miles. Air miles. And let me start by doing Control Enter, see if it works. Here we go. The date column was indeed called dates. So this helps. And then what we have here, so we have first, second, and third, right? But that's not really our data, right? Because if you look at our data, this is monthly. So 1st of Jan, 1st of Feb, and so on. And currently here, it's not like that because we have 1st of Jan, 2nd of Jan, 3rd of Jan. So what we need to do, you basically have 2 options. So one thing that we have here is that there is one parameter here, which is called day first. So first equals to, and I can put this as false. And here we go. Okay, actually not working. So let me put it as true. And here you go. So yeah, somehow, I thought the month was first. But anyway, so this works. So day first equals to true here. And now we have our actual dates. And let me just get like 15 rows so that I make sure that it's working well. And here we go. So we have up until the December and then 1997 start. So everything is good to go. And we can go to the next step. Information about the data frame is always a very good idea. And then as well, what we need to focus is on the index. In fact, that's actually part as well of the challenge. Okay, not this one. Let me try to find it. Here you go. So the first part is on data frequency. So let's focus on the index. So dataframe.index. And we see that we don't really have a frequency. And it's always good to have a frequency. So dataframe equals dataframe and then as a frac. And then here we include an M. But let's see if that works. So dataframe dot index, Control Enter. And here you go. But something changed. I don't know if you noticed, right? So let's have a go and have a look. So dataframe.head, and something is wrong because currently everything is none. So what happens when you set the frequency to monthly? The default is that it goes to the last day of that month. And our dates here are on the 1st. So something needs to change here. What I'm going to do is that I'm going to load the data, and I'll show you here that when it comes to the index, you need to set it to the start of the month. And this is actually super easy. Here you put an M and an S for month start. Let me try again. Here you go. So you can see that they are the same now. So dates. And then here, if I go to my data frame dot head, it's working. So let me get rid of this. Now we have here our daily stuff. Let me get my header again. Let me go to edit and then find and replace. Replace with Y and then replace all. Here we go. And so we have as a comment, so monthly air miles and data viz. Let me change the title to monthly air miles. And here you go. Control enter. Yes. Now we have the Y here. So something needs to change here as well. Let me rename the Y variable. And here you go. So data frame dot rename. And then what I'm going to replace is the air miles here. And now it's going to be called Y. Air miles colon Y. And then in place equals to true. Let me see if that works. Let me get my data frame dot head. So, okay, too many indices for array. And so this is not working. Let me do something else. So what I'm going to do, let me briefly go to chat GPT and zoom in. How to rename a variable in Python. By the way, I'm using ChatGPT 4, but this would also work for the 3.5, of course. But as a big fan of this product, I feel that I kind of need to be on the 4, because I also have a lot of GPTs, because they really help me. So identify the variable. And okay, this is not what I want. So old variable equals new variable. And okay, but rename using pandas. And okay, involves using the rename method. This is useful when you want to change the name of one or more columns. This is exactly what I want. We have the old column name, and then we use the rename method to change the column name. Okay, I forgot this part. Okay, let me get this. So instead of using the in place, so columns, here would be the air miles, and here the Y. So this works. We do Control Enter, and here we have it. Now, visualization. We can see an increase over time. Let me zoom out for a bit. You can see an increase over time. It's not super clear whether the seasonality is additive or multiplicative. You can see that there's a drop here. This could potentially be due to the September 11th, right? Where there could have been a drop. But this is interesting here. Then month plot, right? We no longer resample. And that is because we have our data on monthly level. Monthly air miles. Let's do the monthly seasonality. You can see that there's a very clear seasonality here with January and Feb, and then September, October, November, December on a lower level. So basically we have spring and summer where people fly more, and then autumn, winter, people don't fly as much. So definitely interesting to see. If we put it on quarterly, let's get to know it. Let me get here this Y label, so Control C, and then let me come here, Control Enter, and okay, expected frequency Q, got month MS. Okay, so this is my fault, right? And let me actually do Control Z. Yes, resample Q. And now I need to go back and change the title again. So Control C, and let me change it here, Control V. And here we go. And in general, a reflection, right? So Q2 and Q3 at a higher level of seasonality, Q1 and Q4 at a lower level. Now, let's go here to our decomposition. Period goes to 12 because we have months. Let me do Control Enter. And here we have it. So this is the trend. A bit of an kind of like this S shape, down, up, up. Seasonal wise, varies between 1.1, 1.15, and 0.9 or 0.85, so plus or minus 15%. The residuals, nothing spectacular, a bit of an oddity here between 20 or 2001 and 2002, but everything else is similar. Now let's go here to our autocorrelation, and here we go. We have here that the first, second, third, and fourth, there's some information. And then we also have here some negative, but very close to zero. You can see here that, so this should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So 1 month before, or better yet, 1 year before, we do have a lot of information. This implies a deeply seasonal time series, but this was also something that we could have hinted here, and because this is highly seasonal, and here this is a confirmation. So now we can also do the partial autocorrelation, and hopefully what we would see. Okay, here you go. So we have an error, so can only compute partial correlations for lags up to 50% of the sample size. Okay, let me decrease it. Let's put 30. It's of course more than enough. Requested number of lags must be less than 56. So 30 is okay. Let me do Control Enter. Let's have a look. So we do have here that we have quite a bit of information in the month before. And we also have information 7 months before and 6 as well. So we have 1, 2, 3, 4, 5, 6 negative partial autocorrelation. So kind of like goes opposite. 7 months ago, positive, and then 7, 8, 9, 10, 11, 12. So 12 and 13 also with some information. Again, this signifies a deeply seasonal time series. And as a result, Holt-Winters could actually be a very good model here. Now, this video has been here for a while, so I've been recording for quite a bit. I'm going to take a quick break, then I'll come back for the second part. If I look here at the stamps, so data frequency definitely done, visualize the data as well, but training and test, Holt-Winters, forecasting, and accuracy assessment, no. And this is what we'll focus in the next video. Until then, have fun. Welcome back. Let's focus now on the modeling component of Holt-Winters. Per the challenge, what we need to do is, and let me get it, we need to do a training and test for 12 months, right? So the test set must be 12 months. Therefore, let's have a go at it. So training and test split. And then we do train test equals to. So the first one is dot ilog up until the last 12, comma. And then here, I kind of want everything. And then comma here, data frame dot ilog. And then starting from the last 12. And then, okay, not this. So minus 12 colon, comma, colon again. And let me put the test here to make sure that everything is working. And here you go. So we have the last 12. So this is actually working. And then we build the Holt-Winters model. Let me zoom in a bit as well. Here we go. I knew that we're not in our 125% Holt-Winters model. Model equals to, we use the exponential smoothing. And you could have gone to our practice tutorial and copy from there. That's absolutely okay. Here, I include my train. My trend, you set it to something. If I have a look at it, it kind of, okay, where is it? So kind of feels like a straight line. So this would usually imply additive. And here you go. So add the seasonal component. I set it to multiplicative most of the times, but we can go and have a look at it. And then seasonal periods equals to 12. And then we do dot fit. So this works. And while we're here, so first let me do Control Enter. It's not working. And if none, seasonal must be 1 off. So I did something wrong. Here we go. Okay, I see. I have a space here. Let me try again. Okay, convergence warning. So the model is already telling us that it did not work out so well, but this is fine. We'll focus on that later on. Let's focus now on our predictions, right? Because we need to put it here below. Predictions equals to, we use the model to forecast. And then here I put that the steps equals to the length of the test. And here you go. Let me have a look. So predictions, Control Enter, and we have them here. One thing that you might add here is a rename to Holt-Winters. Here we go. Let me do Control Enter. And here we have it. We have the name. Now we have the function here. And let me get rid, or let me do Control X and put it below. So I activate the function, and then let me put the train test, the predictions, and Holt-Winters remains. We do Control Enter, and let's have a look. So it kind of feels like the forecast, which is green, is accompanying well the test, slightly bit below, but it's doing what it seems to be a good job, right? So MAPE 2.16%. The MAE, of course, is very large. That is because the magnitude of our numbers is also very large. But by the MAPE, you can kind of see it's apparently doing a good job. Can we do better here? So we can give it a try, right? Let me add. So trend is additive. And if you recall, we had 2.16% for the MAPE. And now we have 2.52. So this did not work out so well. You can also see that it's not accompanying so well the yellow/orange line. But so let's go back. We stick here to multiplicative, and we can also change here. Of course, in a more advanced scenario, kind of build a loop. So try everything and then give me the best combination. And currently what we're doing is more, playing around with it, which is also okay. Now let's have a look. So 1.8. So this seems so far the best outcome. So we have another combination. So we have additive. No, we could have multiplicative. I think this is the one that's missing. And here you go. Also 1.8. So nothing changed. So we stick to this. This is working despite the convergence warning, right? We have a very good outcome here. Then the other step here would be, do we need to predict the future? Let me check. So Holt-Winters forecasting and accuracy assessment. So we would be done in this case. If we wanted to predict the future, now that we have it here, let me get the model and with the predictions, right? And let me put it just on this side of predicting the future. Okay, I did not copy the right thing. Let me go back and Holt-Winters. So Control-Shift-S, Control-C. And let me put it here. And let me delete this cell. So instead of train, I put data frame. So this should be enough. You can also put data frame Y, but there's only just one column. So this is okay. Multiplicative, seasonal periods 12, model forecast steps. Here you decide, let's put 12 and get rid of the extra parentheses. We would have the predictions. We still have the convergence warning, but that's okay. And then we have plot the future, and let's get this function here. The Y, so data frame Y. The forecast, it's called prediction, so kind of need to live with that. And then the title is Holt-Winters, and then forecast. Here you go, Control Enter, and it is working. So we kind of see this growing trend extrapolated to the future with the seasonal components. And with this, this is our challenge. You can see that as we have the useful code template and as we build on it, and hopefully it will stop just being a white page. But once we have this, it's so much easier to make it work. It won't work always because some libraries, as we'll be able to see, they have their own way of working, which is also okay, right? Something that we need to learn. But for this one, it definitely works. And we'll continue to play around with this. We'll keep on learning how to make this work. And I'm going to stop talking because it's time that we move on to the next section. Until the next video, have fun. I am super excited to kick off this section on the ARIMA, SARIMA, and SARIMAX. If you've ever wondered how to really predict the future, well, in terms of data at least, I think you're really in the right place. In this section, we are going to kick it up a notch with SARIMAX specifically. But first things first, ARIMA stands for Auto-Regressive Integrated Moving Average. It's really a mouthful, I know, but it's not as intimidating as it sounds. It's like this framework for understanding time series data. We're going to predict sales, prices, even the weather. And just like any type of family, like the ARIMA, there are some other relatives, SARIMA and SARIMAX. Now, each has their own special way of dealing with data, and we're going to focus on them. And what I want to cover now is why ARIMA. So we're starting with ARIMA because it's really the foundation. If you get ARIMA, everything else is easy, right? ARIMA covers 80% of the concepts. And it's really a classical model used in forecasting. And you kind of need to know this because also the concepts here, we can use them in our modern time series forecasting and even in deep learning. There are some concepts here that are used that are very important to understand this time concept. But of course, when it comes to just ARIMA, there is a limitation, right? So we don't have this seasonal concept. We don't have external factors that could affect the data. And this is why we also have SARIMA and SARIMAX. So SARIMA is ARIMA with a seasonal concept, a seasonal pattern. It understands that we have seasonal cycles in our data that repeat over time, like more ice cream is sold during the summer. And then SARIMAX goes even further. It brings in external factors, like maybe a big event or some kind of big sale that boosts the ice cream sales. When it comes to what we'll cover, it's quite a bit. So we'll start by setting up our Python. We'll use our template for useful code to dive into the data, get to know it. In terms of concepts, we also need to understand AIC and BIC. I'll stay for now with the acronyms. We'll get there a bit later. We'll also learn how to predict the future when we have regressors or external factors, like in this case. And it's a long one, especially from a practical perspective, but I think it's going to be fun. At the same time, we're also going to kick it up a notch from a modeling perspective, as we'll be fine-tuning the model to get the best predictions possible. Let's get started. In this video, I'll introduce you to the case study for this section. And picture this. You are the owner of a chocolate retail shop, and your goal is to predict daily revenues. Well, why, you ask? So it's really important that we have a grasp on our cash flow, right? So how much we will earn, so that we plan in advance how much stock we should have. We plan in advance how many people we should have in the store. So if you are to imagine yourself running this shop, it's really important that you understand also why forecasting is relevant. Because for each day, you always need to have some kind of plan. And this is where forecasting steps in, because it allows you to prepare for what is coming, with the goal that our shop wants to be one step ahead. And therefore, we start by predicting the daily revenue. And by predicting the next day or the next 30 days, depending on what we want, it implies that we no longer have that many chocolates that aren't sold. Our staffing decisions are better, right? Because we don't really want people to just sit around. And that implies that people are not working, and this is a loss for the company. And as a result, this would imply as well that we manage our inventory better. So in essence, what we have is that we run our business in a smoother and also, in this case, sweeter way. So what is our task here? We are an analyst or a data scientist, and our goal here is to look into past sales data, look for patterns, and try to forecast future sales. We can also consider big weekends or holidays. So for instance, Valentine's Day should be a very big one for chocolate. And to be honest, right? So it's also very exciting that this case study is with chocolate because, chocolate is amazing. And beyond that, this case study, I think it's a very good one to see how can data actually influence a business. We're not just, using an algorithm, right? We're also going to understand consumer behavior, these seasonal trends, and really try to see that sweet spot between demand and supply. So by the end of this case study, you'll see firsthand how you can forecast the future using ARIMA, SARIMA, and SARIMAX, and also external regressors. You'll get to see how you could actually apply this in a real world scenario. This perfectly mimics what you would do in your day-to-day job. And most importantly, you see how relevant it actually is because it's a skill that can have a real impact. This is it. I hope I'm motivating you, but let's get started. Until the next video, have fun. Welcome back. Let's kick off our practice journey. Let's start by opening here the useful code template, and then please come here to the time series analysis, and then ARIMA, SARIMA, and SARIMAX, and then new, and then Google Collaboratory. Let's take this video to organize ourselves, and yeah, that will actually be just it. Implement this code that we have, and then so we can move on to also learn some concepts specific to ARIMA. Now, let me come here. Let me do Control Shift S, and okay, not this. So let me try again. Control Shift S, Control Shift A, and then Control C. Let me do Control V here, and here we go. So I'm going to keep this structure here for now. And let me start by mounting the Google Drive. And here you go, connect. Okay, Control Enter here. And then, connect to Google Drive. Let's follow those steps. And let's see what else can we do for this video. Okay, sign in, continue. We're going to introduce a lot of new topics, not only from a conceptual perspective, so everything that is related to ARIMA, right? But at the same time, from a modeling perspective, we are going to kick it up a notch, implying that we are going to learn about cross-validation and parameter tuning for time series forecasting. That's it. So let me go here to drive, my drive, then Python time series forecasting, time series analysis, and then ARIMA, SARIMA, and SARIMAX. And let me select here this path, and then Control V, Shift Enter. And the libraries for now, they remain the same. The data is different. So it's called daily revenue. So this is the CSV that we are going to use. And let's go here. So daily revenue, and let's do Control Enter. We're getting an error. So date is not in list. Let's double check. It's date with a lower case d. So let's correct that point. Control Enter. And we get the user warning. So parsing dates in DD, AM, and then year when they first equals false, which is the default. And we should have daily, and currently this is monthly. So first month, so January, February. So what we need to do is we need to come here, because as we see here in our dates, we have the day first. So let's correct that. Let me come here. So day first equals to true. Let me do Control Enter. And here you go. This is exactly what we wanted. So with a year, month, and then day. Next up, let's have a look here at our information. And we have that the revenue, discount rate, and coupon rate, they are all objects. So this is something that we need to do. So we need to make this into numeric. And as a result, let's kick it off with that. And let's just do the revenue first. So what I want is to transform revenue into a float. Revenue usually works well with floats, with decimal cases. If I go to my data frame and then revenue, Control Enter, let's have a look. We see here these little commas. And this is something that is the issue, right? We kind of need to remove the commas to make them numbers. What we do is .str.replace, and then we replace the commas with what? With nothing, right? So we do it like this. And then we also need to tell Python at the same time that we have a float. So as type float. So let me do Control Enter. And we see here that we have numbers. It's a float and everything is working. So let me replace data frame and then revenue, close the square brackets, equals to this. And so this was one thing. Let me do Control Enter. The next one, let me focus on setting the frequency. This is actually something that we don't have yet in our useful code template. Could be very useful. We have daily data, so data frame equals to data frame as frec and a day. And if we had weekly, it would be W, monthly, it would be an M. Now let me do Control Enter. And then the last thing is to change the time series variable name. So in this case, data frame, and then let's do equals to data frame dot rename, columns equals to curly brackets. We change from revenue and then to Y. Let's do data frame dot head because we have made a few changes. And here we go. It's called Y. Now let me do Control Shift S. I want this rename and the frequency. And I'll put them in our useful code. Let me do Control V. And here we have it. So keep on building. And okay, let me do Control S. And now I can return here. And then let's do some EDA, so daily revenues. Let me do Control Enter. We have growing revenues over time. We have a very big spike roughly at around the end of each year. We kind of need to see what this is all about. Could be Christmas, could be before Christmas, could be Thanksgiving. This is something we need to consider. And let's focus now on the monthly seasonality. So this will bring a bit more insights here. And we see that indeed November, this is where we have the peak of seasonality and we have lower peaks. So we have the bottoms in January, Feb, July, and August. And then quarterly, let's repeat. So let's have a look. Again, Q4 as the peak, Q1 and Q3 as the lower quarters. And then seasonal decomposition for revenue data. I may miss one or two comments. I mean, hopefully you can forgive these whoopsies. I'll try to see most of the things that I think are off. But let's focus now on the seasonal decomposition, growing trend over time, and plateauing in the last periods here. So this is interesting. Seasonal, massive peak above 2, so above 100+% increase in seasonality at the end of each year. We also have a decrease here. This could be end of the year, around Christmas potentially. And so this is insightful as well. And we also see a lower values here. So around should be July, August, as we saw before. Residuals. Yeah, we have some outliers, right? We have these dots here that are clearly outside of the norm. So these are interesting as well. Could be worthwhile, of course, to explore some of the regressors here, like discount rate and our coupon rate. They could help us explain what is happening. Let's move on to our autocorrelation. And here we go. Definitely a lot of information that is happening in the past. We also see some light peaks. So 1, 2, 3, 4, 5, 6, 7. So peaks each 7 days. This means that we have some seasonal work here. It means that our data is seasonal, that it repeats over time. Now let's see how it connects to our partial auto correlation. And we see that we have information 1, 2, 3, and then as well 5, 6, 7, or better yet. So 1, 2, 3, yes. 4, 5, 6, so, but 7 again, and then 14 as well. So not just 1 week before, but also 2 weeks before. This is definitely interesting. And then we could have, not so much, right? So 21 and 28, 28 maybe a bit. So there's definitely information from a seasonal perspective. There's also definitely a lot of information in the days that have just happened, so in the auto-regressive. So this means that we have a problem that for our ARIMA model could be good. And model assessment, this for now remains here because we're not going to do it. I'm going to stop this video now. We have covered our data. We understand it a bit better. We have a deeply seasonal time series. We have some outliers, as we're able to see by the residuals, and we have spikes, and these are very interesting from a modeling perspective. Now, let me stop here, and I'll see you in the next video. In this video, we are going to cover the ARIMA concepts. And don't worry if it's a bit too complicated, I'll try to break it down for you in a very simple way. ARIMA stands for Auto-Regressive Integrated Moving Average. And it's really a favorite in the forecasting world because it's very easy to apply. And I feel that the intuition is also easy. So what we need to focus here is that aside from ARIMA, we also have SARIMA that deals with seasonality. And then this crucial layer makes it relevant for everything that has the seasonal cycle. And then we have a SARIMAX that lets us include external factors called exogenous regressors into our forecast. Now, it may sound complex, but it's actually very, very easy to apply. But for this video, we'll focus on ARIMA. It has 3 main parts. Auto-regressive. This part is like looking at the past to predict the future. So we use previous values of our time series to forecast what's coming next. Additionally, we have integrated, and this is where we talk about stationarity. A stationary time series has a constant mean variance and also covariance over time. What does this mean? It means that we have a consistent pattern that we can predict. Now, the integrated bit in ARIMA helps us transform our data to be stationary. We'll cover this. We also have a dedicated section for each of these components. And also in the practice videos, we'll have a special focus on the integrated and stationarity. Last one, we have a moving average. And this one, I think it's pretty clever. So what happens is that we use past errors, yes. So the mistakes that the model has done before, we use it as a source of information to improve future predictions. And then from a more mathematical equation perspective, the equation is ARIMA and is typically represented like this. And this is what it means. So we have the y of t. This is what we're trying to forecast, the value of our time series at time t. Then we have alpha. This is the constant term. It's kind of like this baseline starting point. Then we have the coefficients for the auto-regressive part. This shows how much of the previous value, so y of t minus 1, we should take to our current forecast. And then we also need a coefficient for the moving average. So they measure how much of the errors of the previous time periods we should take. And then lastly, we also have the error term. This is everything that's not explained by our constant, the moving average, and the auto-regressive terms. Now, this might seem quite complex, but have in mind that our forecast at times t is a component of a specific intercept or a baseline, plus the most recent values, plus the most recent errors. Now, let's zoom in into each of these elements. Until next video, have fun. After we have a grasp on ARIMA, let's zoom in into each of them, starting with the auto-regressive, or AR for short. This is, in a sense, the heartbeat of ARIMA, and understanding it is absolutely crucial so that we understand ARIMA overall. So let's see what this is all about. The general idea is that the past influences the present. So imagine that you're trying to predict how much coffee you'll drink tomorrow. A good starting point would be to look at how much coffee you drank in the past few days. That's really the AR component. It looks at the past values of your time series to predict the next one. In our coffee example, the past few days coffee consumption helps us to predict tomorrow's. And how does it work from a more mechanical perspective? It uses lags. In AR, these lags are just previous data points in the time series. Think of a lag like a backward step in time. If we talk about lag of 1 in our coffee example, we're looking at yesterday's coffee consumption to predict today's. And a lag of 2, that's the day before yesterday's coffee influencing today. If we look at the AR as part of the modeling, the AR is represented by the P in the ARIMA model. The P tells us the number of lagged values of the series that you're going to use. So how does it work? Imagine that we have this ARIMA, 2 D and Q are for the other components. So this model means that we are using the last 2 days, lags 1 and 2, of the data to predict the future. And the model looks something like this. So today's coffee is the alpha plus the coefficient for the auto-regressive lag 1 plus the coefficient for the lagged auto-regressive of 2. And so on, right? So depending on how many lags we have, we would have that many coefficients. In this case, we have 2 different coefficients, one for yesterday and another for the day before yesterday. And just so that you have in mind, right? So alpha is a constant, and these, I think it's a delta, right? Or omega. So these coefficients or these characters represent the coefficients. In general, like this auto-regressive represents everything about time series. We use the past to impact the future. And this is very important in time series where patterns and trends over time play a huge role, like our coffee consumption habits. We'll also see that it has a high impact in our chocolate daily revenues prediction. And this is usually the case, right? So if we are to do a problem like this and we don't really have an auto-regressive component, this does not make a lot of sense, right? It means that we don't have information in the past to help us predict the future. And if you're wondering if this autoregressive has something to do with the autocorrelation, the answer is yes, right? Because they're both the same. The autocorrelation helps us to predict how much information is in the past, and the autoregressive models it in the ARIMA model. So they are representing the same field of information. And this was, actually it from my side. In a nutshell, autoregressive, we used lag values of our time series to help us predict the future. And yeah, let's see what integrated now is all about. Until next video, have fun. Let's cover the second component in our ARIMA model, integrated. And this is all part of trying to make our predictions as accurate as possible. So what is integrated, and specifically, how does it connect to stationarity? Think of a stationary time series like a reliable train that goes at a steady pace. The speed, the variance, and the covariance, they are consistent over time. In very simple terms, a stationary time series does not swing wildly. Its patterns and behaviors are stable, which makes it easier to predict what's coming next. And when it comes to stationarity, most of the times it's not. And this is why we have a concept called differencing. So if our data is not stationary, if it's not, steady, like we have seen with our Bitcoin data, so any data that has some kind of trend, we kind of need to use differencing. And this differencing smooths out our data. What happens is that we subtract one day's value from the next. And what we're left is with a series that's steadier and predictable. We're going to see the differences in our practical tutorial, because I want to show you what is a time series and what is a time series that's been differenced, that's been applied this concept of subtracting one value by the next in ARIMA, right? Now let's try to connect here to ARIMA. The integrated is how many times we need to do differencing to make our data stationary. For example, if we have to difference our data once to stabilize it, we're looking at an ARIMA model with an I of 1. Now let's visualize. Let's imagine these 4 charts. The first one, it has a somewhat of a stable pattern over time. This one would be called stationary. The second one, it grows over time. What does this mean? It means that its mean is different over time, and therefore it's not stationary. The third one has varying amplitudes. Think of seasonal sales peaking or dipping in a given month. So its variance changes over time, therefore not stationary. And the fourth has cycles of different lengths. So the ups and downs, you cannot really see how long they go or their amplitude, and therefore this data is also not stationary. when it comes to real-world data, this is very tricky because most real-world data is not stationary. So all financial data is not stationary. Most of revenue or sales data is not stationary. Everything that's a flow or anything, it's also not really stationary. They don't follow a pattern that's super easy to predict. And this is why we use differencing in ARIMA, because it transforms this data that varies over time into something that's more manageable. Now, one question that you may have is, okay, how do I know if my data is stationary? There is a statistical test for that, which is called the Augmented Dickey-Fuller test. It's a way to formally check if the mean, variance, and covariance are constant over time. This is something that we're going to do in the next video, because I want to show you this test, and I want you to have an automated way of checking. And in my experience, right, if you are to just assume that they're not stationary. And have in mind that this differencing is very useful for understanding our data to check if we have a pattern that we can use. And this is a concept that's almost only used here in ARIMA. The other models don't really have this differencing, but this ARIMA has. And fortunately for us, it's something that is automated. We don't really need to think so much about it, as we'll be able to see. Now, let's apply this, and till the next video, have fun. Welcome back. In this video, we are going to focus on stationarity. And we are going to do this with the help of ChatGPT. And that is because I really like to have these functions that, especially when it comes to statistical tests, then they also tell me what this is all about. Because oftentimes the documentation is not really explicit. So using ChatGPT is very, very helpful. Here, what I'll write is write the Python code for, and this is the part where I know the test, for the add Fuller test, and for data frame.y. So this should be enough, and give me the code for interpreting the results. So this is really the most important part, because I can go and I can get the add Fuller test from the documentation, just get one of the examples that they provide and do it. But at the same time, the interpretation is really the most important thing. Now let's have a go at it. So let's see. So we have add Fuller, we have the result. So we apply it to our data frame.y. We get this ADF statistic, the p-value, and then we print critical values. And we do it like this. It's not using f strings like I like, but it's also okay. So let's just take this, and actually not here, but in our other script. Let me do Control V here. And so pandas we have already. Oops, not what I wanted to do. So pandas we have. And then assuming that data frame.y is your time series, which it is, we get the result. I don't really care about this ADF. We just have print critical values. I also don't care so much. So let me get this. The most important thing is, what is the outcome? So I want to have the p-value, and I want to interpret the p-value. Now, I'm not going to go into a whole lecture about what is the p-value. If you have questions about it, you're welcome to share them with me, and I'm happy to provide my view on the p-value and what I know. The bottom line is that the p-value is a threshold to help us do hypothesis testing. In this case, we have a p-value, 0.1, and then interpretation for this specific test is that the evidence suggests that the time series is not stationary. And this is, of course, connected to the null and alternative hypothesis. The null hypothesis is therefore here that the data is not stationary. So this is the status quo. And then the alternative hypothesis, what we'll try to show is whether the data is stationary or not. Now, as I've shared as well, to make data stationary, we do differencing. And what I'll provide now here, so let me go to chat and GPT and say, so write the code to make data frame.y stationary and plot the data frame.y and differenced data frame.y so that we see what is happening. And this should be enough. And let me do control or just enter. And let's see what comes out. We have matplotlib. Actually, do we have matplotlib? We should have, right? Yeah, we have been using plt.show. But one thing that we don't have is the title, ARIMA, SARIMA, and SARIMAX. Here we go. Now, let me come here and let me get the code. And here you go. So here's the code. And let's go to our script. Let's do Control V. Pandas and matplotlib we don't need. But here we are doing differencing. And let me split this. So the plotting and the differencing per se. So Control X and then Control V. And what I want to do here is really have a look at our data frame Y diff. And let me do Control Enter. Here we go. So we have this none here, which is kind of expected because if we do differencing, there's one that kind of goes away. And now let me do some plotting. So we have the original time series. So this should be the one that comes first. And this is the difference time series. And you can kind of see that this trend over time goes away. And what we do have is something that is somewhat stable, right? There's a very clear pattern here. Now, let me go back and let me show you that once you do the differencing, then the data, like 99% of the times, becomes stationary. And if it does not, then you kind of need to do differencing again. But 2 is the maximum, right? I've never seen actually 2. So for sure 3 and 4, that is just too much. And let me go and get it. So it's this one. Let me do Control C. And let me go to our add Fuller. And also let me remove this one. Let me do Control Enter. We have a tiny error. So in for nonce. So let me do dot drop in A here, Control Enter. And here we go, right? So this time the outcome is different. The outcome is that our data is stationary. Now I'm going to stop here. We have more to cover, but for the next practice video, the focus is, okay, do we need to do this differencing and stationarity for the ARIMA? No. But I'll leave that for the next videos. Until then, have fun. time to cover the last piece of the ARIMA puzzle, the moving average component. Now, I'll try to explain it in a way that's easy to get, and I'll use our coffee example that we have explored in the Auto-Regressive component. Imagine that you're trying to guess how much coffee you will need tomorrow. Sure, you can look at how much coffee you drank yesterday and the day before. And, that's really the auto-regressive part that we talked about earlier. But, and I think this is very smart, but what if you also considered the mistakes you made in guessing? Like, maybe you thought that you would need a lot of coffee yesterday, but you actually didn't drink that much coffee. So this is the MA. This is learning from our, whoopsies to make better predictions. Therefore, in simple terms, the MA looks at the errors you made in the previous predictions. It's really like saying, I thought I needed 3 cups yesterday, but I only had 1. So let me keep that in mind for today's guess. And it's pretty neat because it helps you fine-tune your predictions based on the recent surprises, these recent slip-ups. And why do we need it? It's really, again, about smoothing things out. So the moving average helps to smooth out these random bumps in the data. And think of this as a way to, learn from the mistakes and not really take so much of drastic decisions based on what happened in the days before. And at the same time, it's really good for quick adjustments. If at any point, right, we have this recent drop, the moving average adapts to it very, very quickly. It's not just using the previous data, it's also using the previous mistakes. So that is really the moving average in a nutshell, right? It adds a bit of wisdom to our predictions. And in general, you can say that it's kind of like you learned as well, not from what has happened, but also from your own mistakes. Till next video, have fun. Welcome back. In this video, we are going to focus in the ARIMA model. And just before I kick it off, let me do here some organizations. I'm going to take this cell here, so anything that is really related to functions, I am going to put everything at the start. I'm going to call it useful functions. Useful functions. Here we go. Control Enter. And now let me do Control V. And okay, I just got one. Let me get the other one. And I just want the function itself. Control X. And here, let me do Control V. I'm going to activate them. So Shift Enter on both. And now let me come back. And we're still going to predict the future, but just for the sake of organization, I'm going to get rid of this. So this way we have more space and I feel that it's a bit easier to visualize. The first thing I want to do is to split the data into training and test. I'm going to say that the test days equals to, I'm going to do 30. That's fairly standard when it comes to daily data. And then we have that our train and test equals, we go to our data frame dot illoc up until minus test days. And here you go. So this is 1. And then data frame dot illoc. And then we do from from the minus 30 up until the end. So minus test days and then colon. Now let me put here the test so that we can have a quick preview. It's on the month of November, so November 1st to November 30th. Now, we also need a specific library for ARIMA. You can use stats models here, but I have a very strong preference towards PMD ARIMA. Here we go. Let me do Control Enter. And then at the same time, let me prepare here to import some stuff. So I would do from PMD ARIMA, I would import here Auto-ARIMA, ARIMA, and model selection. It's these three things that I want. Let me do Control Enter and no module name PMD ARIM. So I'm missing here an A. Let me do Control Enter once more. And here we have it. Can go back down again. And here we go. Now let me clear out this output. And I'm going to be using PMD ARIMA for the ARIMA model. And at the same time, one question that you may have here is, okay, we have talked about the auto-regressive, the integrated, and the moving average. And what is happening here is that our PMD ARIMA and we'll find, so for the ARIMA model and the best parameters. Now, let me do it here first with you. And here you go. So let me do model equals to, we use the Auto-ARIMA. And then inside here, I'm going to include my train Y. So that is the first one. And then the other one would be seasonal equals to false. So this is how you set up an ARIMA model. And it's just this, very, very simple. And in order to get the output, let me do model.summary. In the next video, I have a deep dive into how this Auto-ARIMA finds the best parameters. It's a very quick way that you can kick a model off. This Auto-ARIMA works for the ARIMA, SARIMA, and SARIMAX as well. So it really works for all of them. So it's very straightforward to making this work. One thing to have in mind is that, and this is what we'll cover in the next video, is really the parameters that make the decision, which for me, they are not ideal because they lack a certain business focus. But this is how they work. It's called AIC and BIC, which we are going to cover. For now, let me show you everything here. You can see the AIC and BIC here. And we can see here the model that we have. It's a 5, 1, 2, 5 lags of auto-regressive, 1 differencing for the integrated, and 2 for the moving average. And then you could also see here the coefficients. The coefficients in itself, they're not the most relevant when it comes to these components. They're interesting when we had here the other components, so the external regressors. That it becomes interesting because it works like a linear regression. But just looking at these parameters, they're not super interesting. They're the same as when we look at the intercept, for instance. So if you want to take one key takeaway is that we look quite a bit from an auto-regressive perspective, and we also look at 2 lags on the moving average. Now, what we need to do is really apply our functions. We start with the predictions, I'm going to call it predictions ARIMA equals to, we use the model to predict, and then the number of periods is the length of the test. And very similar to our simple exponential smoothing, what happens with the ARIMA is that we also get the same values most of the time, right? So it's something that tends to go to a straight line. It doesn't go immediately to a straight line, but it gets there after a few days. And this is so because remember that we're going 5 days in the past, right? So it takes a long time until, not a long time, but it takes 5 periods so that we are just using our predictions for the forecasting. Now, let me take one of our useful functions, which is our model assessment. Let me do Control-C. And actually, I want to go all the way to the bottom. Here we go. Let me clear out here the output. Okay, I'm just clicking on stuff that I don't want. And code here for the model assessment. And let me do Control-V. We have our train test predictions ARIMA. And then the chart title will be ARIMA. Let me do Control-Enter. We have a tiny error. And yes, because so if you look here at our train, you see that we have quite a bit of things. We have the Y, discount rate, coupon rate, and we kind of need just the Y. So train, and then let me put some square brackets, Y, and then same thing for the test, Y. And here we go. So this works, and you kind of see our green line. I mean, maybe you don't see it. Okay, let me zoom in. Our data is until the end of 2023. So let me go and do 2022, and then to the right of the single quote, colon, Control-Enter. And here we go, right? So we completely miss out here on the spike, and this is an issue, right? So we're really not doing well here. And if you look at our MAPE, 24%, and then we have a massive MAE and RMSE. If you see here that they are quite disproportionate, so they're very different, the MAE and the RMSE. This means that, of course, with these big spikes, when we have big spikes that we cannot really explain, then the RMSE will usually be much higher than the MAE. So as a conclusion, right, so our ARIMA model does not really work out here. As I've shared before, if you look at our data, we have a deeply seasonal time series. So we kind of need SARIMA. And just before we get to it, I also want to cover the AIC and BIC. So until the next video, have fun. In this video, I'll cover the AIC and BIC, and as well how they connect to our Auto-ARIMA function. Now, let me kick off by specifying what they mean. So AIC stands for Akaike Information Criterion, and BIC is Bayesian Information Criterion. And you can think of them as KPIs to help us choose our model. And the way that they do is that they score each model, kind of like talent show judges. So what is basically happening, right? So the AIC and BIC give us a score, but how do they do it? They take into account two things: goodness of fit, so how well the model fits the data, and the complexity of the model. think of it as the number of parameters used. The AIC specifically is all about balance. So it wants a model that fits well, but doesn't go overboard with too many parameters. It's like making a great cake with the least ingredients necessary. The BIC, on the other hand, is very similar, but it gives a harsher penalty for models with more parameters, right? So the BIC will prefer something that's simpler. The AIC doesn't have this penalty. It focuses a bit more on balance. Now, how to connect this to our Auto-ARIMA? For each model that the Auto-ARIMA tries, so the Auto-ARIMA tries different combinations of the Auto-Regressive, the integrated, and the moving average. And for each, it computes the AIC and the BIC. And the model with the lowest value is usually considered the best choice. Now, there's a bunch of pros of choosing a performance or a process like this, because first and foremost, it's pretty straightforward and it's objective to compare different models across one KPI and making the selection process a bit more data-driven like this. Same time, penalty for complexity. So this penalizes overfitting in our models. And the focus is that we get a model that generalizes well. And as well, flexibility. So the AIC and BIC is a type of KPI that you can use across many different models, not just the ARIMA, SARIMA, SARIMAX. For instance, you can use it for segmentation. Of course, you can also use it for regression analysis. So it's something that you have on your toolkit and you can use it everywhere. From the cons perspective, they don't really give you a good or bad score. To be fair, that's true for most of the KPIs. So one thing to have in mind is that the AIC and BIC is only meaningful when you compare it to other model score. As well, we don't really have a business focus. A company would mostly focus on an error metric. So how far away is our model from the actual values? And currently, it's really about goodness of fit, which is partially that, but also complexity. And a business wouldn't care so much about it. And then lastly, we have information loss. Because we are penalizing complexity, there's a chance of dismissing models that capture important nuances in the data. Now, let's zoom in on the process. So the function runs through several different combinations of P, D, and Q parameters and calculates. And again, it's really about trying the different combinations and see which one is the best. And the way that we would pick is the one with the lowest value. This is important. It's the one with the lowest value. Therefore, to sum it up, AIC and BIC, they're very helpful because it allows us to try different combinations of parameters in a way that's automated. You saw how easy it was for the ARIMA model. For the SARIMA and SARIMAX is the same. It's very, very easy. Now, you kind of need to consider that it's not perfect, right? We should mostly focus on error, which we will do eventually. So focus on the MAE and the RMSE and MAPE later on. But for now, this is fine. And we can assess our model like this. Until the next video, have fun. In this video, I'll cover ARIMA, which, as I've shared, is ARIMA, but has a seasonal component. It's really this extra added layer of real world that we need in order to forecast with the highest accuracy. The SARIMA is really the ARIMA with seasonality, even in the name. And this seasonal component will also have some influence in the way that we do the modeling. So let me cover first, why do we need SARIMA? In very simple terms is because most data as some kind of seasonal patterns. If you think of ice cream sales peaking in summer, or that you need more coffee during winter, like we do need to factor that in. And for that, we need SARIMA. From a modeling perspective, we also have the PD and Q, and this remains the same, but we kind of have to have the seasonal axis, and that is uppercase PD and Q, which the ARIMA will find out. So we have this P for the seasonal auto-regressive order. We have the D for the seasonal differencing order, and then the Q for the seasonal moving average. And then lastly, we have the M. So this is the number of periods in each season. This one is very similar to the exponential smoothing when we're picking 7 for daily, 12 for monthly, and so on. Now, let's zoom in here on how SARIMA works. So first, we do have here the seasonal differencing. Just like the differencing in ARIMA, we also, in the seasonal data, we apply this differencing to stabilize these patterns, to make the data stationary. We have as well the seasonal auto-regressive. So you go back, X number of lags, but from a seasonal perspective in the past, and see until when you have information to look in the future. And then as well, you look at the seasonal moving average. So this is the seasonal patterns, but you look at the forecasting errors that you have made recently. In practice, it can really be a bit of a balancing act between finding the right combination of parameters, but fortunately for us, we have the ARIMA, which can swiftly do this, and later on, we'll also do it in an automated way by writing the code ourselves. Wrapping up, SARIMA, a very powerful tool. From an application perspective, you'll see how easy it is to make it happen. Seriously, it is really, really simple. But let me go from words to actually actions, and let me show you how to apply SARIMA. And until the next video, have fun. Welcome back. Let's apply here our SARIMA model. And I'll do mostly copy pasting. That is because we have really covered everything that we need. Let me get here our modeling. So this part, the train and test set kind of remains the same, or remains exactly the same. Then we have the predictions and the model assessment. Let me do Control C. And here in the SARIMA, let me do Control V. Let me clear out the output and let's make the changes. So let me have here model SARIMA, just so that we have some kind of distinction, and as well model SARIMA summary. We will no longer have seasonal equals to false, and we need to set here the frequency of our data. We have daily, so M equals to 7. And you can have more information. This is actually not such bad documentation, but let me see if I can get it and open in tab. There's a lot here that you can include, but please don't be intimidated by this. There's some stuff that you can obviously ignore. This is so that, there's a lot of stuff to actually use here, but I'm giving you not just the essentials, but to be fair, I've never really used anything. The one that you can use is this stepwise. And what this stepwise is doing basically is that we are not really testing all combinations of P, D, and Q. And now we'll have 6 different parameters. We're not really testing them all. We're using this stepwise algorithm that kind of like just looks at parts of the combinations. It infers that some combinations are not working and just uses this parameter. I'm going to keep it to true because I think is really the best option. But if you really want to not be cutting any corners, you can set this stepwise to false. Now, let me come here and we have the model SARIMA. And let me change here SARIMA, predictions, SARIMA everywhere, model SARIMA. Let me put this running because now that we have the SARIMA model, it should take a bit more time. And so prediction SARIMA, this remains the same. Now I change here the prediction SARIMA for the model assessment and as well the title. Now, this should not take a long time, but I'm going to take a quick break here while this is running. And in what will be a few seconds, I'll come back to check the predictions and the assessment. Okay, we are back. This took around 5 minutes or so. Here, let's have a look. We have here that the best combinations will be this 3, 1, 2, and then 2, 0, 2. So 3 lags of the auto-regressive. And let me actually just also share here what these lags mean, also seasonal and non-seasonal. So the 3 lags of seasonal implies that we go 1, 2, and 3. So we go 3 days before. But for the seasonal lags, what we do is that we go 1 seasonal lag and 2 seasonal lags. So we kind of go this M parameter, which for us is 7. We go 7 and 14. And this is how it works. Now, let's continue here. We have the predictions. So let me do Shift Enter. And then as well, we have our model assessment. And if we go and have a look at it, we are completely missing the spike, but we kind of have this seasonal part here. The weekly seasonality is there, but we're definitely missing this big spike. And this is because with SARIMA, we just have one seasonal component, which for us, we choose as weekly because we have daily data. And we miss on this yearly seasonality, which could have captured this component here. Potentially, if you set it to 365 here, this M, you can get a better outcome. But it's standard to use 7. So this is really your best option. And let me also just compare. So we have 24.15, and actually with SARIMA, we got a bit worse. If we look at the RMSE, we have 1, 2, 1. Okay, let me get it here. Or better yet, it's actually easier or looks a bit better if I get this part and put it below. And we kind of have, okay, this is also not working. Let me add here some bullet points. Bullet points you add with this asterisk and space. And here you go. We actually get an improvement in the MAE and the RMSE, which are better KPIs to look at. Even though the MAPE is slightly higher, this improvement in the MAE and RMSE, this is the important part to highlight. So we are getting better, but still, we are very, very far off. And in the next video, let's work on the SARIMAX. So until then, have fun. This video, we're going to go one level up to SARIMAX. So what is it exactly? We have the SARIMA plus the exogenous variables. And this is where the X is coming from. And essentially, it's literally the SARIMA plus these external factors. Well, it's simple, but it's also very, very powerful. Because imagine that you're trying to predict ice cream sales. So with SARIMA, we kind of consider the past sales and the seasonal trends. But what about temperature? What about a hot day that could spike sales? SARIMAX allows you to include these external factors like temperature in the forecasts. And that's really the X factor, pun intended, these exogenous variables. These are variables that allow us to include external factors to explain our time series. In our ice cream example, could be weather conditions, holidays, or even nearby events. SARIMAX takes these into account, which gives you a more holistic view in what affects the data. From a process perspective, we're not really adding any new component to our SARIMA, but these exogenous components, these X. And the model analyzes how these variables have historically affected the main time series, and this will hopefully produce a more accurate prediction. And that's really the first pro. We should have a higher accuracy using SARIMAX if we have these external events. At the same time, we also have greater insights because we can also study these external factors that influence our data. When it comes to the cons, we have complexity because this adds a layer of complexity, right? We need more data. And at the same time, we need to consider the data availability. We need to have both the historical data and also this future exogenous regressors in order to use it. In a nutshell, using SARIMAX effectively means carefully selecting the data. Again, we don't want to make it too complex. As always, if we can do it in a simpler way, that is usually better. Therefore, you should consider what to include very carefully and really try it out. See if we can add more and more accuracy as we add these external factors. Let's see how to apply this. Until next video, have fun. Welcome back. In this video, we are going to create our SARIMAX model. We are going to use some stuff that we have used before, specifically for building the model. But before we get there, we need to work on the inputs. If you recall, when we were playing around at the start, we saw that our data is just objects. And at the time, we took care of the revenue, but we did not take care of the discount rate and the coupon rate. Therefore, let me copy this part here, transform revenue into a float, and bring all this way back at the end. Here you go. So let me change the comments, transform regressors into floats. And we go and we get our discount rate. Let me do data frame dot columns here so that we have a quick preview. Let's get our discount rate. And here we go, here. And then as well, the coupon rate. And then let's see what we need to change as well. So coupon rate and Control V and Control V. If I am to have a look, so data frame dot head, they have this percentage. We kind of need to remove it. So instead of the comma, the percentage, and as type float. And let me do data frame dot info at the end so that we just make sure that we're doing it right. And here we go. Everything seems okay. They are now all floats. Let me get rid of this. The next step is that we need to also do this training and test split for the regressors. Let me come here to the point when we did it initially. So split the data into training and test. And Control V, here we go. So test days 30. So this works. And now what we want, and let me get here our data frame dot head again. What we want is we want this column and this one. And what we need to do is comma 1 because it's index position 1. But we need to do 1, 2, 3 because the third one, so this element here on the right, this one is excluded. And let me do here as well, 1, 2, 3. Let me get our test. And here you can see that we have our discount rate and our coupon rate. So we are doing it correctly. Now, more copy pasting. Yay. Let me get here our model building. And here you go, Control Shift S, and then Control and Select, and also the model assessment, and then Control C. And then let me bring it all the way here to the end. First, let me decrease this output. And now let me do Control V. And okay, I unselected everything. Let's start again. Let me get our ARIMA. Select, select, select again, Control C. Copied 3 cells. Let's go here, Control V. Or not working. Okay, now yes, working. And let's change what needs to be changed. So model SARIMAX. We have train equals to y, right? So this remains the same. M equals to 7. And let's do x equals to. And okay, oopsie. Okay, we need to do some stuff again because I made a tiny mistake. So here, let me do exoc train and exoc test, because otherwise we'll get an error. So we change everything. So this is 1. And then we had here the inputs at the start. So let me run that again so that we have this train and test split done once more. And here you go. So it appears to be working. And now let me go to our SARIMAX. We have taken care of the regressors. Let me delete this one. So split the data. And let me change here. So split the regressor data into training and test. And this should be working. Let me do Shift Enter. And this part I don't need. Train Y, X equals to exoc train. And here we go. So exoc train. And this should be enough. So model SARIMAX dot summary. Let me do Shift Enter. Hopefully it will run. Now let me change. Let me add an X everywhere. And we kind of need to change here the predictions because we need to include here our exoc for the test. But let me just change here the model assessment with an X. So X's everywhere. And then the changes here for the predictions. So we still have the number of periods, but you add this X equals to exoc test. So fairly straightforward. Nothing really too complex. It's really about adding this X element. And this will run now for a few minutes. If it's like last time, it will be around 5. So I'll take a quick break, have a sip of water, and I'll be back, which for you will be in a couple of seconds. Okay, we are back. Let's have a look. So we have 212 and then 202, very, very similar to the previous SARIMA model when we had 312 and 202. In general, this extra layer of exogenous regressors led that we don't really need so much information in the past. Now that we have our model, right, it's really about assessing it. Now we have our predictions, SARIMAX. Here you go. We have them here. And then we do our model assessment. And here we have it. We have that our MAPE is now 19. So it has really improved. Same thing for the MAE and the RMSE. So what to conclude? So this part, it needs to be considered. We have not. And so far, I don't really want to focus so much on the exogenous regressors and how to play around with them. We can leave that for the future sections. I want to focus on process and techniques that we can apply. And one thing that we kind of need to have a look here is we assess the last 30 days. But what is the performance of the model in the 30 days before and the 30 days before that? Is it good? Is it bad? These are the questions that we need to answer. We should not just assess a model over one period. We need to assess it over more periods in time because we need this robustness to tell us whether our model is good or bad. And at the same time, we need our model to work well throughout the whole year. And even if it does not do well over, this specific period, it doesn't mean that it is bad. It means that it is bad in these 30 days. In the next video, we have a very important concept to cover, which is the cross-validation with a focus on time series forecasting. Till next video, have fun. Cross-validation is a fundamental concept for forecasting because it provides credibility and robustness to our models. The key idea is to repeat the experiment or testing in different situations, so different times of the year, to make sure that the model works. Therefore, what we will do is to have numerous training and test sets. For instance, we'll add the test set to the training before we actually make the predictions. And we'll do it several times. Specifically for time series, this is very important to test a model in different seasonalities because since the seasonality is different throughout the year, just because it works well or it does not work well in a specific part of the year, it doesn't mean that the model is overall poor. Now, zooming in on cross-validation, there are two types of cross-validation. In this slide here, I'm showing you what is called a rolling forecast, because each time we add the test data to the training data before we make the following test. The other type is that each time that you cross-validate, you also trim the training set. And in this case, you always keep the same length here of training data, and you just shift it to the right. This is called the sliding forecast. My general preference goes towards the rolling forecast. If you are not using the data, maybe it's because it's not worth it, and therefore it should not even be there. But if you are assessing the model and then you should always use all the data. That's at least my assessment, because if it's valuable for training and for assessing, it should also be valuable for the forecasting of the future. And if it's not, then it should not even be there for trial and error. To recap, cross-validation is very simple but a powerful concept to build any forecasting product. There are two types: rolling and sliding. Rolling means that we are always extending the training set by including the test data from the previous run. And the sliding means that we absorb the test data for the next run and we discard the same amount of data from the most distant past. Let's see how this works with our model. Until the next video, have fun. Welcome back. Let's do cross validation. And here we go. And let's see how we can implement this in a very, very simple way. First, we kind of need to define the model to do cross validation. Let's build our model. And let me do model CV here equals to. And we are not going to use the Auto-ARIMA, right? We have really found these best parameters according to the AIC and BIC. And this is what we are going to test. But what we have already is this function, this ARIMA function that we are going to use. So let's go there and let me start building. So I use ARIMA. And here, so parentheses, and then I set the order of the non-seasonal components. So order equals, and then it was, and let me come here, 212, and the other one was 2027. Let's go back, and let me put it here. So order is this, comma, seasonal order equals 2. And then let me go back up. And where is it? Here we go. Now let me do Control C. And coming back down, parentheses, Control V. And here we have it. So the model is done. Now what we do here is that we set the cross-validation rules, so to speak. So cross-validation equals to, and now what I use is this model selection that was also imported. And then I use the rolling forecast CV and parentheses. Let me get some help here so that we have a look. Let me get all of this and let me get this part and let's have a look at the documentation. And we have here 3 components: H, the step, and the initial. The H is the forecasting horizon, so how long in the future we want to predict. We have been using 30 days. Step. So this is the size of step taken to increase the training sample size. Let me zoom in as well. And this is basically, we're going to set it to 15. So every 15 days, we predict the next 30. And then we have the initial. Personally, I usually do it for the last 6 months or the last 12 months. It is really something that I prefer to do. I don't really care about, testing this, 2 years ago. Doesn't really matter. So let's do it and let's set these rules here. We have that our H equals to 30. Our step, we're going to do it every 15 days. and the initial. And one simple way that I do it is data frame dot shape and then 0, because this gives us how many rows we have. And then I just do minus 180. And this is enough, right? So I just set this minus 180. So these are the rules for the cross validation. Let me do Control Enter here. And then what we have here is the inputs for the cross validation. And we'll get a score equals to, we still use the model selection dot cross val score. Here we go. And let me open here the parentheses. And now what I should do here is that I include the inputs. Now let me open in tab. Let's see if I can do it now. Okay, this is not being super helpful. And let me see if we have it here. Here we go. So we have here the estimator. So this is the model. We have the Y, so the time series. We have the X. So these are the exogenous variables. Then we have the scoring. So this is the metric that we are going to retrieve. We have here as well the CV. This CV is the rules that we have just set. And then we have verbose. So this is how much the model should tell us. And then we have an error score. So value to assign to the score if an error occurs in estimator fitting. If set to raise, the error is raised. If a numeric value is given, then we have a warning, and basically we just move on. So I always like to give it an error. So if there's something wrong, just put an error there, move on. Don't, stop, just continue. So let's do it. We have all of this to do. We need to include the model. So Y equals our data frame Y. Here we go. Or better yet, not my data frame, but rather let's continue with a train Y here. And then we have that the X equals our exog train. Then we have that the scoring, or better yet, actually data frame dot Y makes a lot more sense here, because let's include all of the data. And here let's define a new exog, because we had done it here. But let's just get the columns 1 and 2. So let me copy this part, or better yet, this should be enough actually. Let me do Control C, and then let me put it below. So here instead I do X equals 2. I put my data frame and then columns 1 and 2. So just for you to see, if I do Control V here, we get an error. And here we go. Let me put the colon there, and now you see, right? So we have all of the data. So this works for us. So let me put here colon. Then after the X, we have scoring. I have a preference towards the mean squared error. Here we go. So let me do Control C. And I have this preference because, as you saw, right, when we have our data, we have this big spike. And it's important that I get the spike right. So it's important that we also have a metric that represents that wish to have the spike done correctly. Then CSV equals to CSV. Verbose equals, I put it to 1. And then the last one, error, score. And here I just put quite a bit. That's a lot of zeros, but that's fine. So we do this, and now it's going to run. I'll come back once this finishes its run so that we can have a look at the output. Alrighty, we are done. It's actually much faster. I expected a few minutes here. But if we are to have a look at the CV performance, first let's check. So this is the output. So CV underscore score. Let me do Control Enter here. And we have this. So for each of the forecasting periods in which it was tested, which was 1, 2, 3, 4. So 4, 8, 11. We have an outcome. And what we do here is recall that we have the mean squared error. So first, let's get an average here. So numpy dot average. And I actually don't know if we have the numpy already. So numpy is not defined. And so let me do import, not here actually, let me keep our template here tidy and organized. And here you go. So import numpy as np. And let me also put this numpy here in our template because it's important. Here you go. And now let me go back. Let me do Control Enter here again because I forgot if I did it. And let me get our average. And big number, right? But have in mind that we need to do numpy.sqrt. sqrt. And here we go. Let me do Control Enter. And we have this value. Now, let me compare this value here. Oof, this is a big one, right? So all of them are very big. So this one is 10 million, 0.4, so 10.4 million. And this one is 4.3. And let me just store this. So RMSE equals to this. Print with an F string, the RMSE is, and then RMSE. And with, let me do it as an integer because it's such a big number. We don't really need decimal cases. Now, what can we interpret from this? We can interpret that our model is really poor in this period of the year. And this is why we have such a huge RMSE. But then when it comes here to this longer period, so this longer cross validation, then the outcome is this, right? So we have such a big improvement. Now, what I want us to focus from here on out, right? Up until now, this PMD ARIMA focused on tailoring our model to the AIC and the BIC. And I don't care about that, right? We should be results driven. We should focus on improving and getting higher accuracy. Therefore, I will do this parameter tuning with cross-validation, and we'll try to find the optimal values for this ARIMA model. So we're trying to find the optimal parameters, and we will mostly use this structure here, but let me not spoil it any further. Let's start in the next video. Until then, have fun. Parameter tuning is key to going from a good forecasting product to a great one. Granted, the programming that we'll do can be a bit challenging, but I know that we can do it. Additionally, you'll have this template that you can use and reuse, which makes it very easy to replicate. First things first, why do we need parameter tuning? The thing is that we have a lot of innovation in analytics that brings to our models some tailoring, some customization. But at the same time, since the possibilities are there, it kind of requires us to go the next step, to use this customization and tailoring to bring one solution, one optimal set of parameters for each model that we use in order to bring the highest accuracy. From a process perspective, we start by defining the parameter options, and after we run the model, we measure the accuracy and we save the error. In a nutshell, it's nothing more than what we have done before. The thing is that we just need to repeat this several times and in an automated way. Going into the details, so imagine that we have our auto-regressive, we do lags 1, 2, and 3. We run each model, we measure the error, and we save it. Let's say that this is the error. We would then pick auto-regressive 1, so the lag 1, as the optimal parameter. I think overall, from an intuition perspective, it should be okay to understand what is happening. We try a different set of combinations and we pick the best combination to use for our model. To sum it up, parameter tuning is all about finding the optimal set of parameters for our problem in order to achieve the highest accuracy. Now let's apply this in Python. Until next video, have fun. Welcome back. Let's focus here on parameter tuning. This is where we are now combining our cross-validation and we'll find the parameters ourselves and we'll do it based on the RMSE and not the AIC and BIC. I need a function here, so let me bring it all the way here. And from sklearn dot model selection, and here I'm going to import the parameter grid, and this is actually a relevant one, so Ctrl+C and let me put it in our template, and let me go all the way back down and we can kick it off. For this video, we'll just focus on defining the parameters. Here we go. Param grid equals to, and we start with a dictionary. So the P, and have in mind that we should kind of like take these values here as a baseline. So 212 and 202, so 7 remains. So we should take these values here. Also have in mind that it's 6 parameters. So this is really exponential. So let me start here with 1, 2, and 3, comma. For the D, let me do 0 and 1. And here you go. So 0 and 1. And for the Q, let me give it 1 and 2. 1 and 2. Comma here. For the seasonal lag, so P, let me give it 1 and 2 as well. And comma, and we go to the D. Here, I'll just say, you know what? It's always a 0. So no combinations there, because this really becomes exponential. So especially at first, let's take it easy and like you can really play around with this, but have in mind that the time that you wait is always exponential here. So Q, and let's put 1 and 2, and just for the sake of it, let me add a 3 here and here instead of, or you know what, let's do 1 and 2. Also, another thing, right, is that the more lags you have, it also takes much longer to do something that has a lag 3 than something that has a lag 1. So our time also increases in that sense. Now, we have this done. We do grid equals parameter grid, and then I include my param grid. And just so that we have in mind, so if I do a list here of the param grid, here we go, and actually not of the param grid, but of the grid. Hopefully this will be done soon. Actually, I don't know why it's taking so long. And okay, let me stop it. Oh, cell is already running. Okay, this is odd. But yeah, I want to have a look at how many we have, just so that we have a brief overview of what we are doing, so that we have in mind how long. So if you consider that when we're doing the cross validation, it was 37 seconds. Have in mind that we should kind of like multiply these 30 seconds by the number here of options. Now, okay, something is odd. Let me actually come here and let me interrupt the execution, because yeah, I don't really know why. Okay, also did not work. And let me then yeah, I kind of need to restart the session. So this stopped. The sad part is that I think we need to go back and run everything. And then let me see if our directory is there. So this works. Let's install pmd ARIMA. Let's do everything, also the exploratory data analysis. And yeah, let me get also this stationarity. Won't take a lot of time. And so this, we don't need this ARIMA. I'm not going to run this because, as you recall, it took quite a bit of time. So hopefully I can actually go back, because I should not really need anything. So we're doing the cross validation. Let me do here the param grid. And here we go. So you see here that we have a list of a lot of possibilities. And if I do the length here, then we get how many? Here we go. Control Enter. We have 72. So 72 with, 30 seconds, right? We should wait 35 to 40 minutes. So it's still an okay amount of time. But, the more you add here, right, it really, really grows. And with this, I'm going to stop here. In the next video, we are going to do our parameter tuning loop. And until next video, have fun. Welcome back. Let me start this parameter tuning loop by defining here our strategy. What we need to do is that we need to build the model with a set of parameters. So this is step 1. Then we need to evaluate the model, and we need to store the error. Fortunately for us, we have done everything. So it's really about taking what we have done and making it in a way that goes through this loop. And what is very, very easy, for instance, let me get here our CV performance, and let me get this part. So let me start here with the cross validation. So Control C and bring it down. So this is part of evaluating the model. Let me remove this comment. And the other part is this with the inputs for the CV. So these two are the same and they are part of the same assessment. Storing the error. So this is part here of this RMSE. Here we go. So I'll put it under storing the error. But we are going to do it for each of the set of parameters. So we start here by having this RMSE list. And let me start with an empty list. And what is happening here is that each time we compute the RMSE, and then what we do is that we go to our RMSE list and we do append the RMSE. Now, what we're missing here is building the model. So let me go here. When was it? Here we go. We have our model. Let me do Control C and Control V. And what we need to understand is that we kind of need to go through each of these parameters. And what we will do, and this is where I start to build our loop, and we will do here 4 params in grid. So we go through each of the sets that we have here in this grid. And let me do here a tab. And we go here, we build the model. And now here we need to make something that is iterative, right? So that each time changes. And we do params here and we do the P. So this is one, and let me do Control C and let me replace everywhere. And then we'll make the necessary adjustments. Here you go. And here we go. So P, D, and Q. And then we'll have uppercase P, uppercase D, and uppercase Q. Now, let me give it some space here. And just to recap here, right? So we are building the model each time with a new set of parameters. We have the cross-validation defined. And in fact, this could actually be outside because it's not really dynamic. But it's okay. Let's remain it here. It also does not really waste a lot of time. And then we have the score. And then we do the average of the score, and then we store this error metric. Now, let me do Control Enter here, and we have an error. Name model is not defined. And here we go. And let me do model underscore CV. And actually, okay, so when we're doing the cross-validation, I did something wrong because it should have been the model underscore CV. So actually, before I do this, let me do the cross-validation again because there's an error there. And here we go. So the score on this train test. Okay, estimator fit. Okay, so we have definitely something wrong here. Yeah, we get a lot of warnings apparently. And if we do our CV performance, float object has no attribute D type. So let me get here our CV underscore score. And you can see that we got a warning for each of them. So this is an issue here, right? So it yielded an error for each of them. Now, this became even a bit more interesting. We have this as a D-type object, right? So this tells me that there was an error here. No. This model CV remains the same. The Y and X remains the same. CV as well. Nothing really changes. So what this is telling me is that while we're building these models with these errors, we're getting this huge error, which is not really an issue because we want to do the parameter tuning. And if we have a big error, that's okay, at least for some parameters. But what we want is that we find the optimal parameters. And we have here our model here. And let me do Ctrl Enter to see if this runs. It does not, so that's an issue. So estimator fit failed. The score on this train test float object has no attribute D-type. So we're also getting an error here. And okay, this is where we actually take everything. So let me do Ctrl C. Let me go to Chat GPT. And we have the code. And let me get the output. And let's see what comes out. So the important thing is that in the end, we're able to solve this. So hopefully, this will be something that can be easily taken care of. And yeah, this is actually something that I was not really expecting. So if I am to have a look as to what really happened, it's a bit unclear. So we have 4 params in grid try. I'm not a big fan of this try, so this is a pain. And what I would like to try while ChatGPT is there thinking. So if I am to have a look here, so we have our ARIMA, so 212, and then we have the model selection, rolling forecast CV, and we have the error score. Now, what I don't really get here is why this comes as an object when this should be a value. And at the same time, let me have a look. Okay, this is becoming far more complex here. So we have the RMSE list, we have the grid, and it started using stats models. Okay, let me read with you. So type error unsupported operand types, string. This error typically occurs when the model expects numerical input but receives string data instead. It's crucial to ensure that all input data to the ARIMA model, both y and any exogenous variables x, are numerical. If your data frame contains non-numerical columns, so dates or other string values, you'll need to exclude them from the x and the y, or convert them into numerical format. Okay, model fit warning. This warning indicates that the model fitting process encountered an error, which, based on the previous error message, likely stems from attempting to perform operations on incompatible data types. And then attribute error, float object has no attribute type. This error suggests that NumPy average CV score returned a single floating point number, but then the code attempted to access D-type attribute that doesn't exist on a float. This error is a bit misleading because the real issue comes from how the error scores are handled when the estimator fit fails. And okay, let's address this one by one. And let's make sure, so if we go here to our code, we have our y, and let's start there. And let me do our data frame y. 1795, type float 64. And then we have, or let me just do data frame and have a quick preview. And we have our dates, right? And then until the 30th of November. And okay, interesting. You see, we have the discount rate and coupon rate. So this is where my issue is coming from. That is because potentially when I had to restart the kernel, then, of course, every transformation that we did was wrong. So let me come back, and when we had our SARIMAX, here we go, and let me transform this. So everything is a float. This is very good. And let me come back. And so our cross validation here, we don't really need it anymore. And let me do Shift Enter, Shift Enter, Shift Enter. And okay, user warning, but it's a different one. So yay. Okay, this is okay, right? So it's telling us non-stationary starting auto-regressive parameters found using zeros as starting parameters. This is okay, right? The important thing is that we are now, or this actually works. So this is the most important thing. Now we have our CV score. We don't really need it. And as soon as this is done, hopefully it does not take much longer than this, and it shouldn't, but we have our CV performance that we can have a look. And we can make a new assessment based on these values, because in the end, we should have maybe some different values, and we can compare it once more to our 10 million something. Now, because we have such a big spike, I don't really expect a different conclusion here. I expect us to have a much better performance as we test the model in different parts of the year. But of course, in the end, this is still something that needs to be addressed from a business perspective. I won't super focus into it. The goal of this section is, of course, aside from SARIMAX, really focus on this pipeline of the cross-validation and the parameter tuning. I'm going to leave this part on really looking at the data and the errors for the later sections on time series, or better yet, on modern time series forecasting, for instance, on profit and so on. And that will be a big focus. But for now, I really want us to go and do this cross-validation and parameter tuning. Now, I've been talking a lot, so I'm going to take a pause, and I'll come back when this has run. Okay, we're back. So the outcome of the cross-validation for that initial model, let me clear out here this output, is 4 million. And so actually, let me confirm. 4.4 million. And this is very similar to what we had before. So definitely much lower than the 10 million. So we have the same conclusion that our model is much better in the other periods of the year. That said, now we can return to our parameter tuning, Shift Enter, and then model, and this should work now. We're doing our CV score, and yeah, this is where our issue stemmed, right? So our issue came because our data was not really perfect to be as inputs. Now, I'm going to stop this video now. I'll come back in the next one. So also, you're welcome to start the next one and just see how long it took. But yeah, have in mind that 30 minutes minimum, 40, that is the most likely outcome. Till the next video, have fun. Welcome back. Let's wrap up this parameter tuning part. I can tell you that this took around 2 hours, so I guess that is quite a bit. That said, you can, for instance, omit here not include the 3 because they take a lot of time. So let's check now what are the best parameters. So checking the results and checking the results here. What I'm going to do first, so tuning results, I'm going to transform our grid into a data frame. So pandas, data frame, and then grid. And then I'm going to add to our tuning results the RMC list. So RMSE equals to our RMSE list. And then we can have a preview. So tuning results, Control Enter. And here we have it with a 72. Let's build here into an interactive table. And let's increase the number of results per page. And then here we can click on RMSE. We see that the minimum here is the 401. So with 102 and then 201 model. So you can see it's not super complex, right? It's actually even, I think, even simpler than the one from the Auto-RIMA. That is definitely a good result. You can also see that you have this 201 and then 201 as well. They're basically the same. So you can see that for the first, actually for quite a few, the difference is not that big. And on the other hand, the one that's very complex, it got really high errors. But yeah, this is how we can really evaluate and choose. So this is definitely good news. We have improved. We have a new set of parameters. Let me close this. And here I'm going to save the best parameters. And one way, so we go to our tuning results here. And what we do is that we try to find the minimum. So tuning results from the RMSE, and let me include here single quotes, when this is the minimum. So tuning results RMSE and then dot min. So if I do this, don't forget the parentheses. You can see that we have here these values. And one thing that's always easy to do is to transpose. Let me do Control Enter. And here we can get them from the index. So that makes it much, much easier. So best params equals to this. And just so that we have them there as well, let me export here and see the output. Control Enter. And this will make our lives much, much easier. With this, I'm going to stop now. And in the next video, we'll continue because now that we have our tuned model with the best parameters, we can definitely predict the future. Until then, have fun. Welcome back. Let's focus now on predicting the future. And the goal of this video is on the setup, right? So make sure that we have all the inputs ready. And then in the next video, then yes, we actually predict the future. First and foremost, so prepare inputs. So we have here that our Y should be our data frame and then Y. So this is how we have it here. We have, just so that like we are in a sense, preparing, make sure that we have everything. I kind of like to have this approach. Then data frame dot iLock with all the rows and one, and so the first and the second column, so 1, 2, 3, and forgetting here a comma, Control Enter. So this is prepared as well. So let me do X equals to this. So prepare data inputs. Let me add that as a comment. And then here what I can also prepare as well. So fetch the best parameters. So for instance, we have our best params, and let's start there. And if I do dot lock, and let me get here the first P, Control Enter, here we have it. But there's quite a bit of information here. So, and when it comes to these type of parameters, they're also integers. So if I just do int like this, let me do Control Enter, we just get here the 1. And this is exactly what we want in the end. So let me do Control C, and let me repeat this in total of 5 extra times. And so P, D, and Q, and then uppercase P, uppercase D, and uppercase Q. And here we repeat. And let's go, almost there, P, D, and Q. So this part is done as well. And what we need to have is these future regressors here. Because have in mind that everything that we use to explain the past, we need to predict the future. And you can see that I have here this discount rate lag 1. This is for a different exercise when it comes to feature engineering. And we are going to focus here in our discount rate and the coupon rate. So let me go here and let me get the part where we get the data. So let me do Control C, going back to predicting the future. And here I do Control V. The file name is future regressors. Let me confirm that. And yes. So future regressors dot CSV. Let me do Control Enter. And we see that we don't really have a revenue. The dates are here, but one thing that you should definitely watch out is that this is a tricky data set, because we have here that our discount rate is already divided in, and it is 0.18. So what we need to do, and is that here I'm going to call it prepare the regressors. We know that, so this is our X, right? We have 34.27, 1.09, and we can see here that everything is divided by 100. So having the same magnitude is extremely important. And okay, made a whoopsie here. This would have been data frame underscore future. And here as well. I don't think we'll need data frame anymore, but otherwise I can still get it and run everything. So data frame underscore future here dot iLock. So this is one possibility, and we get 1, 2, 3. Let me do Control Enter. Not defined, so I need to define it first here. And now let me do Control Enter. So this part is here, and then if I do times 100, then this is, in a way, something that is very similar to what we have. So let me call it X future equals to this. Let me do Shift Enter. And I think I'm going to stop here. I think we have all the inputs. We have the data, we have the parameters, we have the future regressors, and now it's really about tuning our model. And until next video, have fun. Welcome back. Now we have 3 things left to do. The first one is build our tuned SARIMAX model. We need to do some forecasting and we'll do some visualizations. Let's start with our tuned forecasting, or better yet, tuned SARIMAX model. Here we go. Tuned model equals 2. And here, if you recall, we need to use the ARIMA. Where was it? In the cross validation. Now, let me get this part here. Control C, going back to predicting the future. And let me put it here. So Control V. Now, instead of these values here, what I do is that I replace these inputs, and this way you don't really need to care about the values because it's dynamic. P, D, and Q, 7 remains the same. And let me do Shift Enter. Here it is. Now we focus on forecasting. We use the tuned model here to predict. And inside, we have the number of periods, which equals to the length of the X future, comma, and X equals the X future. Here we go. Let's see what comes out. We get an error. Model has not been fit. Yes, okay. Forgetting about that, right? So tuned model dot fit, we have a y and x equals to x. Here we go. Let me do that. And then we focus on the forecasting. Taking a few seconds to run, but yeah, there's just a few things that I want to show you. And this is why I am not really copy pasting the model building, because I need to show you here. So we have here that this is kind of working. We have our data. And then what we do next is that we go and we store our predictions equals to this. And here we go. So let me do Shift Enter. And now let me go to the useful functions and let me get here the plot future. And at the very end, we are going to do data visualization. I put here the plot future function instead of forecast should be called predictions. And then the title will be SARIMAX. SARIMAX. Here we go. Control Enter. And here we have it. A bit difficult to see. So let's focus here after 2022 with a colon. And here we go. You can see that at the very end, this is the forecast. The last thing I want to mention here is that there is one thing that is left to do, but I want to show you in later sections, which is to do feature engineering. As I have hinted here with the future regressors, not here, having the lagged values of investments is always a good idea in order to help us predict our time series. It's really always a good idea, even if anything, just to give it a try. But for now, I'm not going to include it because I think that we have learned a lot in this section. But as you learn to do feature engineering, you're always welcome to apply it to SARIMAX. In fact, it is encouraged. I'm gonna stop here. I hope you had some fun, and all of these concepts on cross-validation, auto-regressive, parameter tuning, all of this can be used later on in future sections as well. So let's continue. Until next video, have fun. First and foremost, congratulations on completing this section. I know it was a long one, and we really went and did a lot of steps when it comes to the modeling implementation. That said, that's actually a pro for me that we have this PMD ARIMA library that allows us to do it quickly. The fact that we have these functions already that are capable of doing cross-validation, that makes it far more appealing to beginners. Moreover, now that we have this general structure of Holt-Winters and SARIMAX, we know that we can follow it to a certain extent. Granted, it won't work always, but the logic is really there. Additionally, though SARIMAX is an old methodology, it gets really good results, as you were able to see. On the negative side, SARIMAX is not always great with long duration time series. To be fair, that's the case with most forecasting models, so not such a big deal. Moreover, when a forecasting model is highly dependent on the auto-regressive term, then it usually means that it's not super good for long-term forecasts. It's very good for the short term, let's say the next few days, next few weeks, but when it comes to a longer forecast, it's not as stable. Moreover, when it comes to dealing with regressors, SARIMAX uses simple linear regression, which means that if we have multicollinearity or non-linearity, SARIMAX will struggle a bit. Finally, SARIMAX does not allow more than one seasonality in the data. You saw that it would be ideal that on top of the weekly seasonality, we would also like to have this yearly seasonality. This was also an issue with Holt-Winters, but from now on, and as we move to techniques in modern time series forecasting, this will stop being an issue. But anyway, I think SARIMAX is great. It's very, very easy to apply, and it's really one of those go-to forecasting models that we all need to know. Till the next video, have fun. Whoa, can you believe that we are done? It was a massive effort from your side. So give yourself a pat on the back. And now the gifts. First and foremost, the materials are for you to keep and use. Please use and reuse them. They're absolutely ready for work. I'll also leave a link or several links in the description for some free ebooks that I have. So prompt engineering, also a very cool one, or on conjoint analysis. And there's more, right? So your journey does not stop here. Feel free to leave in the comments what are you looking to learn, and I'm more than happy to point you in the right place. That's it, we are done, and I'll see you in the next video.